Hello, hello, hello.
Good
Ah,
afternoon.
awesome. Good afternoon. Hi, Michaela, and good afternoon, Allison. You guys are getting it. Thank you. See, I need that. I need that in my life. Either way. So yes, thank you, Allison. Good afternoon. Thank you. Oh, I missed. Oh, I'm sorry. I missed Key. Good afternoon, Key. My bad. Good afternoon, Bradley. Also my bad. Hi, Michaela. Good afternoon, Dante. Good afternoon, Juliana. Hello, Sade. Hi, and good afternoon, Samantha. Good to see you. Good afternoon, and I get it, I get it. Good afternoon, Mario. Good. I'm not going to say good afternoon, Luigi. Like, that's too obvious, right? Obviously, I wouldn't do that. Plus, that's obnoxious. I wouldn't do that. It's a good thing I didn't do that. Okay. Although I've only seen, hi, Dennis. It's all right. Thank you. And I know he already knows that his friend knows that I've seen like one movie in the theater in the last 15 years or so. That's a slight exaggeration, but not much. And the one movie was the Mario movie, which I thought rocked. But okay, anyway.
Good afternoon.
Good afternoon. Was that, I believe, that was, I'm going to guess that that was, wait. Oh, that's Christopher. Yes. Oh, and video. Nice. All right. Good afternoon. I'm not calling attention to it, but I totally am. And good afternoon, Samantha David. Okay. Oh, and more people are coming. All right. Oh, Houston, we are making contact. Oh, and Michaela has an avatar. He's heard it all his life. Yeah, I believe you have. All right. Well, let's not even get started on the Yaverbaum jokes I've heard of my whole life. Like, before Pong and Pac-Man and Space Invaders, there was the famous video game Yaverbaum. Look it up. I'm lying. Don't look it up. How cool would that be though? Okay. All right, more people are coming. Hello, hello. I said good afternoon, Samantha. We're just getting rolling here. Did I miss anybody? Okay, okay. Good afternoon, Alexis. Thank you. Awesome. Good afternoon. Hello, Panina. Thank you. Awesome. Okay, good afternoon, Christina. Awesome, thank you. And who else am I? And good afternoon, Valentina. Thank you. Okay, awesome. Awesome. Oh, and Dante's showing video. Yes, and Christopher showing video. And that doesn't mean you have to keep it the whole time. That's so exciting. And it's like so stupid that I call attention to it because that just makes it worse for you. I know. I'm sorry. But no, thank you guys. And if you leave at any moment, I totally will completely notice and call attention. No, I won't. Good afternoon, Samira. Oh, and Valentina. Oh my God. See? You see what I'm saying over here? It's like one thing leads to another. Oh, and Samira. It's crazy. I mean, as a reward for this, I might even teach physics today. I might even try to teach you physics. Like, this is so exciting. Okay. Might. Well, yeah, this is like and another. Okay, we might actually be breaking records here, people. Okay, I'm not gonna dwell on it, but I am. It makes me very happy. And just please understand again, I know you all met my younger son yesterday, and he's a piece of work. I have only all of his good parts are thanks to his mother, but I also have an older son who's your age. Well, I mean, who's 19 and in college, and like he went through the whole Zoom thing. Like, the whole Zoom thing started when he was a junior in high school, and it was awful for him. Like, and he never showed video. Like, I mean, I believe me, I get it. I think I get it. Anyway, okay. And there's a lot of avatars. Thank you. I totally appreciate it. I see it. Okay, we're gonna start. So we have, again, you can stop. I hope you're beginning to see that you really can stop me at any time, or you can give feedback at any time. You can redirect at any time. I'm here to paddle, but the more that you steer, the better it is for and then the videos went away. Okay, well, no, that was good though. That totally, okay, sorry, I didn't say that. They didn't. I don't even know what I'm talking about. No, all those people should totally submit for points and be proud of themselves. And I totally know that they're still paying attention. I know they are. Okay. So you could stop me at any time if there's something I'm forgetting or if there's an agenda item. I think to bookkeeping things first. I mean, so we're going to get, to some physics and stuff today. Bookkeeping things first. Bookkeeping things first. Today's Wednesday. So it is true that now there's new homework that is due Monday. It's very mathy. It's about the math that we're using in this course, that we need in this course. Some of it is review for some of you, some of it is new for some of you, but it's not a diagnostic. It's just the math that we need, okay? And it's like a way to get it out there on the table. So you do have to do it for Monday. It's a little bit long. It is long, but you have a whole weekend, blah, blah, blah. Someone asked a very good question yesterday. I think it was after class. Someone asked, like, how do you do the 5-step method for things that are so mathy? Fair question, but like to all that you do, you absolutely do. So for example, in those first couple of questions, if you've looked at it I'm talking about homework 2, math methods, which is due this Monday. First couple of questions are like, you're given a function like x equals a cosine omega t, something like that. What would you do for a diagram? You would draw a cosine graph. Like honestly, like and here you draw a cosine graph, you would make t the independent axis, the horizontal axis, lowercase t. You would make x the vertical axis. You would label your axes. You would make that cosine shape. And here's what I mean by graph in physics. A graph in physics is a sketch. It's a rough sketch. It's mostly meant to convey fundamental shape, the fundamental relation between the two variables, right? You don't plot a whole bunch. You don't have to, get out Excel or the thing you use in lab, which I love, but oh my God. I can't believe it just.
Desmos.
Thank you. Yes, thank you. The man's paying attention. I have to open up a portal for that. Yeah, Desmos. When I say sketch a graph in a homework assignment, you don't have to get out Desmos or anything. Thank you. Or anything like that. Here's what you do have to do. Here's the requirements for a graph in non-experimental physics is the axes with labels, key point, like T, X, maybe even the units, T parentheses, seconds, X parentheses, meters. Okay, that's key to show. Then the general shape, and then you label a key point or two. Like you don't have a million dots or anything like that. You just have a sketch of a shape, but you label a key point or two. Specifically in this case, I'm talking about now helping you with exercise 1 in the homework number 2, right? We use that cosine graph, and I believe, stop me if I'm wrong in the chat, but I believe the cosine function that is given to you is x equals capital A times cosine of omega t, or it might be x equals x naught omega t.
No, that's it.
Is A, okay.
X equals A cosine omega t, yeah.
Okay, thank you. Thank you. So this is a double lesson. I'm about two reasons I'm about to say this. So first of all, if you think through that in your mind, if you remember that the sine of 0 is 0, and therefore the cosine of 0 is 1, right? Then that means for that function, x equals a cosine omega t, if you plug in 0 for t, right, you'll get cosine of omega times 0, even if you don't understand at the moment what omega is, or you think you don't understand what omega is, although it sounds like a lot of you do already from lab, which is great. But even if you're like bumping on omega, you know that the cosine of anything times 0 is the cosine of 0. Cosine of 0 is 1. So when t equals 0, most definitely x equals a, right? Like a is the initial value of that cosine. I mean, if a, it's a multiplier, it's a scaling factor on what would otherwise be the pure initial value of a cosine graph. The pure initial value of a pure cosine graph would, of course, be 1 because of what I just said. So, but then it's multiplied by a. So this is a long way of saying maybe 3 things. 1, I'm saying the y-intercept of that cosine graph most definitely is the value a. So you would definitely put that in your little graph, like for your original diagram of this first problem in homework 2, even though it just looks like a math exercise. And even though, or especially because I did not provide a diagram, that's like all the more reason that you want to. So you would make a little cosine graph sketch. You'd have the axes labeled. Then you'd have that y-intercept labeled as a. Okay, and there's going to be one more label in there in a moment. I'm going to tell you, but let's dwell on this for a second. There's 2 reasons you would label that a. 1, because the whole point of any graph in physics is as long as as long as the axes are labeled, and as long as the general shape is clear, and as long as at least one key point, such as a y-intercept, is labeled to give you a sense of scale, then the graph conveys everything that the graph is meant to convey in physics. Like that's all you need to see the entire relationship that a graph is meant to convey. You wouldn't even have to label one point, except that by labeling the one point, you're telling us the scale of that graph. So number one, that's like a procedure for providing a graph, is labeled axes, one key point labeled, and general shape. But the other thing that came up in a number of homeworks I was looking at, and I want to address to you, one of the reasons that we provide a diagram at the beginning of every problem in physics or proof in physics, whatever, the reason we provide a diagram at the beginning is because physics isn't just math. Physics is physics. Physics is about space and time in the physical world. Math is the language, right? So the diagram, you'll know that you gave a good diagram. You'll know that your diagram served its purpose if every single letter, every single variable or constant that is used in the presentation of the problem and the solution of the problem, if every one of those letters, such as A or such as omega, is presented as a label in a diagram, then what the diagram has done is defined all the terms of the algebra that's yet to come. This is another part of this whole standard that we're trying to reach, which is producing independently clear, self-contained physics, right? If you do a good diagram and you label everything in the diagram with a letter that's then used in your solution, once again, then what you've given me is a self-contained physics proof of something. It's not just a response to a teacher exercise. It's something that stands alone and could teach someone else something or prove something to someone else, whether or not they know me or are in the class. That's the goal. It's all like a road to publication or research or whatever. You're just trying to produce real physics here. So, okay, so you make a little cosine graph. Again, this I'm just like trying to start you off on homework 2, and then we're going to obviously go back to the homeworks that were on here. You make a little cosine graph, and then you want to label omega also for the same reason. You're going to want to label omega. Well, where's omega in that graph? I can tell that some of you do already understand this from lab, and some of you may remember from math classes. So I'm just going to say it now as a hit. Some of you might have to think about what I'm about to say. Some of you might want to write it down and then screenshot it for one of the portals. But where's omega in that graph? Well, if you really think about it, if you really think about that graph, a cosine graph, again, I'm sorry, I'm off. I'm talking about homework 2, problem number 1 right now, just to get you started. If your function is x equals a cosine omega t, right? If you think about it, you make a cosine graph in the independent horizontal axis is t time, then that means the space between any two crests of that graph, the interval between any two bumps, any two peaks in that cosine graph, that interval is the amount of time for one cycle of that graph. That's known as the period, right? Or often known in physics as capital T. Again, I'm saying a lot. I think you already sort of know this from lab and from the board meeting today, which I heard went very well. That's awesome. So that period of time from one peak to the next peak, that period of time for a full cycle, that's capital T. That's the space between two humps in the cosine graphs. So you make a little bracket and you label that between the two bumps, and you label that as capital T or whatever. And by definition, if you really think this through, we'll get to this more formally, but if you think it through, you'll realize that 2 pi radians divided by that is what we mean by omega. I'm asserting that. I'll explain it more later, but I would put that as a label in your graph before you do anything further. Like, what does omega mean? What omega means is 2 pi, because a full cycle of a cosine graph is 2 pi radians, right? So 2 pi radians per one period is the rate at which that cosine graph is cycling. Omega equals, you can make it a label. Omega is defined to be 2 pi divided by capital T, that interval between two bumps. So once you put that label in there, now you've got a picture that is fully defined, every term of the problem. Then you can go ahead and start taking derivatives or whatever the problem's asking you to do. I'm going to go one step further. I'm going to stop. So that would be step 1, DFP, diagram and fact pattern, right? Step 2 is, what is the question? You got to write down what is the question. Most of you are, some of you are not. You could, right now, you could just consider it a hateful part of my personality that you just have to indulge. But if I ever on your homework, I write WIQ question mark, I'm saying, what is the question? I need to know the question before you, in your words, before you go any further. So of course you can do that here. The question, I believe the first question is, what is dx dt? Like, what's the derivative of that function? Okay. What would be a GDP for that? What would be a GDP? I'll tell you right now. I think there's at least 2 GDPs. I mean, you could get very deep if you wanted to, but in order to take the derivative of that function, well, first of all, you might write down the definition of derivative, depending on where you are in calculus. That might be a helpful thing to write down to get you rolling. But let's even assume that you already understand how to take a derivative and you know the definition. Okay, fine. For sure, in order to take the derivative of x equals a cosine omega t, in order to take that derivative, again, I'm just saying this because I think most of you get this. You can slow down the tape later and watch it again. But to take the derivative of x equals a cosine omega t, you have to understand it 2 steps in your mind, even if they go really fast in your mind. You got to know how to take the derivative of a cosine, right? And you have to know how to take the derivative of a function, i.e. you're not just taking the cosine of t, you're taking the cosine of omega t, right? So literally the GDPs here. Oh, sorry. Yeah, I'm sorry.
So we can for the GDP, we can basically say, basically defining derivative of a trig and the chain rule.
I'm sorry. I just got a different direct tie to distract me. Sorry. Start again. Say again.
It's the 2 steps are basically finding the derivative of trigonometric functions and chain rule.
Exactly. Yeah, that's exactly what I'm saying. And ideally, especially anybody who, you or anybody who feels at all comfortable with calculus or likes calculus, what I would literally do is write each of those things down. I mean, I really, okay, actually, I'm going to just do this right now just to get, hold on. I'm just.
Hi, Professor. Sorry for interjecting, but
yeah, I see your, oh, I'm sorry, go. I see your direct message. I was just about to, hold on 1 second. Okay. Okay, wait. Okay, sorry, Sarah. Yeah, I got you. Thank you, Sarah. I see I just responded to you. I'm good if you're good. I get it. Okay. What was it? Okay. And I know I'm already getting myself. So what Christopher just said is right. I was about to, yeah, I guess I'll write it down just to be clear what he's saying. These would be, okay. We'll get back to the other, just so I can close this loop and not leave everybody. Whoop. Okay. Again, for anybody I'm confusing right now, this is like a slight sidebar here. I'm just giving you a hint to start off homework 2, what I believe is the first question. What I'm suggesting to everybody, and I know, and by the way, I'm just doing this quickly just to get you started. And of course, we'll go over it like once it's turned in. But I'm very aware, if anybody's still listening to me, I'm very aware that the question is phrased like x equals a cosine omega t. So your graph is going to have t and x in it. But notice when I go to GDP, just again, this is as like a larger suggestion of how to do physics. When I go to the GDP, when I go to the general definitions and principles that are relevant here, first of all, yes, I agree with Christopher. The general definitions and principles that I'm thinking of right now that we totally need in our mind in order to solve this problem, we need to know how to take the derivative of cosine. We need to know that it's negative sign, right, in general. And we need to know how the chain rule works in general. So partly to express these as general mathematical ideas that are just true whether or not this problem has begun, I'm on purpose writing them out as y and x the way you would see them in a math class. I want to say this is on purpose. It may slightly confuse some people at first because the problem is particularly about x and t. But those are almost like numbers to me. That's the particularity of the problem. I'm backing up in step 3 and saying, you know, what I know in general to be true, or what Christopher knows, or whomever knows in general to be true in calculus is trigonometric derivative, this one that we need, and how the chain rule works, that one down there. So we write them as general. Okay, so anyway, this is just a long way of saying, yes, please do the 5-step method for the math exercises. I mean, if they're easy, then you'll be a little bit boring to do the step method, but it'll still break it down and help you. And then when the problems get to realms that you don't know, the method will be more helpful. But anyway, so that's what's going to be due on Monday is homework 2. We have to get back now to the other homeworks. I will say that you guys are doing a great job so far. I mean, I think you and anybody who's listening and I are sort of caught up with each other right now. Like I think tons of you have turned in homework 1A and 1B. Some of you have already even turned in revisions on 1B, which is great. Anybody who has not gotten even though homework 2 is due Monday now, if you have not gotten a 35 on 1B, you absolutely still could turn in a revision to it. If I told you, if I made marks here and there, I just make marks. I don't necessarily like break them down into individual points because it's homework. But if I made marks and gave you a way to improve it, you're welcome still to do that. You can also email me and ask, blah, blah, blah. My suggestion is start getting to, if you got any kind of score that's in the 20s or higher, first I would start trying to tackle homework 2. Just don't fall behind. But absolutely, I will still take any revision or update on homework 1B. Or if you turned it in and you're like, wait, yeah, but he gave me a cursory number, but I don't really see many marks on or whatever. Could you give me more feedback? You can just send me a message and say, yeah, I don't see much feedback. Can you look at it more closely now that the due date is passed? Sure. Okay, but let's move on. So there's no door that's closed on homework 1B, but we're moving on to homework 2. Obviously, I'm going to start going over these things in a minute. But I think you're all doing very well. Tons of homeworks have come in, and I think most of them, I think you've all gotten numbers back on everything, which is good too. Oh, one other thing. When I write on the homework, you know, WIQ question mark or GDP question mark, hopefully you're seeing what that means. Those refer to steps that I think are missing. And that's the point of the steps. It's partly like a grading rubric as well. But there's one abbreviation that I do use that is not anywhere in a sheet anywhere. So I'll tell you right now, I guess I'll just write it right here. There's one abbreviation that I do use, I want to alert you to. If I put WWW, what it technically stands for is like what, why, where from. And what that's really code for, that's when you write down an equation that's probably legit, like probably true, probably even relevant, but it's an equation that we haven't seen yet in class. So it's legitimate, it's probably right. It might even get you the right answer. But if it's an equation that we haven't seen yet or derived from first principles or isn't a first principle, you know, if it's a derived equation that we have yet to derive, that doesn't mean you can't use it, but it does mean to me you got it from somewhere. I don't need you to cite it. It's not that. And I'm not saying you can't get it from somewhere, but if you're getting a new equation from somewhere, like you went on the web, or maybe you got it from lab, which is always a possibility too. But if you got it from somewhere, you have an extra responsibility to break down that equation and show how it derives from things that we do know in the class. Like everything has to build logically in physics. Nothing can just be out of a black magic. So if you write down an equation that you got from a web, that's fine. But you really have to go to extra effort to show me that you totally understand that equation, which means you see how it follows from things that we have established as true in the class. So WWW means expand more, so that neither of us thinks that you're cheating yourself in any way from actual understanding. That's what, again, with all these comments, if you ever got anything less than a perfect score where any of these comments, it just means that's a thing you can do and you can resubmit and get more points. It's not, okay. I think that's clear to people. Last thing on that too, mechanically speaking, or electronically speaking, there's always a little bit of a glitch, a thing with Google Classroom that I don't fully understand, but in general, my experience is, in general, if you've turned something into Google Classroom, and even, or especially if you've gotten a grade on it, in general, there's a way where you could just upload a new file. You can upload a new attachment, even to something that you already got a grade on. You can upload something new, submit something new without taking down the old. And if you do it the right way, which I think is just add new attachment, I'm never totally sure, I'm not on your side of it, but if you submit something new without taking down the old, generally I get a notification, I see that that's happened, and I can see this new revision and I can give you more points. I can change the grade, I can update the grade. I can even give you a higher grade than is the maximum grade. Like if you showed video today and you upload it, and fine, and then you show video again tomorrow, you can upload again a new screenshot to the same portal. And, and I'll give you another 8 points or whatever it is. Even if it says that the maximum is 8, you can have 16 points, blah, blah, blah. So please do that. If it fails, then let me know. But what we always prefer in this class is don't take down old work, add new work, and I will add new points. But let me see your train in both cases, okay, to everybody. A lot of people are asking me that. Whether it's with the participation point stuff or actual homework, the more you could just upload more and let me, because if nothing else, I'm just seeing how hard you're working. Like, why would you not want me to see, and you can always direct my attention, say, look at the most recent one or whatever. Okay, hopefully, oh, it is. Okay, wait, it is. I forget someone, okay, thank you for the direct feedback, indirect message somebody, but I actually totally forget. I totally forget what I said that you're responding to, but okay, direct chat person, thank you for saying it is. Could you, thank you. I forget what is, but okay, cool. Okay. We're now, if there's no other questions, I think, I guess I should warn you too, it's likely that by next Wednesday, a week from today, likely there'll be some kind of an official practice midterm will have been posted by then. And it's likely that in lab a week from today, what you'll do is have some sort of review session or go over solutions or questions and stuff to some sort of practice exam that will have been posted by then. I'm just saying this informally right now. Okay, we have to nail this down exactly in the background, but you can be prepared that by Wednesday, before Wednesday, you'll have a practice exam posted and you'll be like sort of walking through it or trying it out. And you'll probably take it as a practice for no grade, but for practice in lab on Wednesday. And then you'll have time to then trade, and you'll probably have some time to work with one another. And you'll have some time where Professor Talley will like go over some solutions and help to the extent that there's time. So you'll be able to like practice a midterm Wednesday, and then an actual midterm will be posted shortly thereafter and be due something like Friday night or Saturday night at midnight. Like, I don't want to ruin your whole weekend, but I do want to give you time. So this is a rough, I'll post the details in Google Classroom just so you can plan. You should assume that there'll be practice documents posted next week. You'll have a time to practice them for no grade on Wednesday in lab, and you'll be able to get a sense of what's going on. And then it'll be posted shortly thereafter, like that night or the next night. And then you'll have till Friday night or Saturday night, something like that, to take home the exam and do it on your own time, just so you know. Okay. So, all right. So, but I'll put formal details to that in Google Classroom. I just want to let you plan for adding a new document. It's just, great, direct chat person. Thank you. All right. So someone in direct chat is confirming that if you want to just add a new document to something that's already there in Google Classroom, you just upload new doc. Don't do anything else. Great. I've always wanted to know that. great. So that's what we should do. We almost never should you remove any work that you've already done, because it's work that you've already done. It's like totally, you should be proud. Okay. Well, thank you, Samira, for asking, and thank you for being public. I'm being a little unclear because I'm not 100% sure yet, but you should plan. Okay, I'm informally saying that oh, cool. Okay, so I'm informally saying that the exam will be posted by Thursday night, 8 p.m. and you'll have till like Saturday night at midnight, something like that, to do it. In other words, and that's on purpose so that you can have all of Saturday work on it, but so that it doesn't actually ruin your whole weekend. Okay. So I'm informally, I will adjust this slightly. This is not exactly right, but something like the exam will be posted Thursday night, by Thursday night, 8 p.m. And it'll be due back to me midnight Saturday night of next week. This is all of next week. Okay. It'll be something like that. I'm going to check in with, I might get more of your feedback on Monday to see if that works for everybody. Okay. But that's like the rough draft idea. And again, I'm saying this again to everybody, say it's posted by 8 p.m. Thursday night. You will have already seen a document that will be extraordinarily similar to the actual exam. You will have already received it a couple of days before then, and you will have like walked through it and tried it to some extent in lab on Wednesday. So by the time it's actually posted, it's not going to be a shock to your system. It'll look very familiar. That's the idea. And you'll go home and do it in your own time, in your own way. Okay, and thank you. Okay, so thank you, Michaela, for this feedback. Yes, so I'm making no firm promises right now, but actually why I'm throwing this out right now is to get this kind of input from people like you. So like Michaela is asking, is it possible to extend to Sunday night? So I'm not 100% making a promise yet, but I am saying, okay, I'll take that into consideration. And it is totally possible. Yes. Like if I hear from enough people, like if everybody else said, no, like I might, but yeah, I'll take that into consideration. And okay, wait, please do means, please do extend to Sunday night. Okay. Well, that's 2 votes for that. Okay. Oh, okay. Well, we can do this. Are we doing this now? Okay. I mean, if, okay, I'm listening and it's not really cool. Fine. Okay. Well, here we go. Okay. Again, part of the reason I'm not making a firm promise right now, I mean, look, I'm more likely to do that than not. Like that's probably fine. The only reason I'm caging my bets and saying this is informal right now, and we're not like writing it in stone, is some of you are more comfortable like voicing your needs in public than others. It's still, I want to say to everybody, some of you can still direct chat me or what, direct message me, or you can text me probably and say like, actually, that really freaks me out. Like I actually really don't want it to be Sunday night. I can't do what everybody wants, but I do want to hear from everybody. And I don't just want the first voices or the loudest voices to dominate. So I'm taking all this into consideration. And if nobody says to me that they mind having their whole weekend ruined, that's cool by me. So fine. I mean, so probably this is what's going to happen, but I'm just saying for those of you who are quieter and are hearing all this and are quietly panicking and feeling like, wait, the train's leaving the station. I haven't had time to think about this yet. You still have time to think. You can still reach out to me privately. Also, last thing, as long as we're talking about this now, okay, whatever decision I end up making, whatever we do is for the whole class. But sometimes there are exceptional circumstances. If you're a person who has exceptional circumstances, you reach out to me exceptionally. We'll talk about your exceptional circumstances. And sometimes I can accommodate them. I can't every time, but sometimes I can. We'll talk about that when we get closer to here. But what we're trying to figure out now is like, what's the thing that's going to apply as the class rule? But okay, so right now it sounds like we're roughly expecting that an exam will be posted by Thursday night, 8 p.m. and will be due back Sunday at midnight. I mean and if we do that, by the way, there's absolutely no way I'm grading it like you won't have it back the next day. That's for sure, but that would probably be true anyway. So, okay, so this is informal. You could play back the tape or whatever. Informally, you can start planning and expecting that like it'll be posted Thursday night, due back Sunday night. That's fine. That's great. Thank you for the feedback. But again, if you have an issue, let me know privately, and that will either affect the whole judgment or I'll be able to accommodate you privately. Okay. Or I mean, individually. Okay. Okay. Let me pause for a second. We're going to switch. Let me pause for a second. Okay, sorry. Okay. So we are going to shift gears. I'm now, oh, okay, wait, I'm looking at the things are happening in the direct chat. So just pardon me. That's a really good, wow. Yeah, that's a really fair question. Okay, so I'm embarrassed. All right, so there's a question in the direct chat. It's really a fair question, but it's kind of embarrassing. So the question in the direct chat, obviously I'm not going to mention the person's name, but it is a great question. Basically, someone's asking in the uploaded videos on YouTube, are there timestamps of like when a certain portion of a question is being worked on? Those would be really helpful. I know, because I know it takes me really long to get to things and stuff like that. That would be super helpful. There are not. Part because I have to get these up really fast because I have not yet figured out an efficient, easy way for me. I mean, I have to sit through all the videos in order to make those, unless you know something I don't, and you can privately help me. As far as I know, I would have to put those in. And I would have to sit through and watch myself for hours to do that. And I'm not prepared to do that at this point. If I could find out a fast way to do that, or someone wants to help me, then I would. I think that'd be really helpful. But no, sadly, right now they're not. But here's a point to everybody. Also, if you have checked out the videos or you haven't noticed yet, one of the reasons that I keep the whiteboard dominating the screen in such a big way like this, which has advantages. Oh, I'm sorry. The question someone's asking privately: are there timestamps on the YouTube videos to like tell you like when I get to a certain question or not? And the answer is no, there aren't, even though that would be really helpful. And I regret that there aren't. I just don't have the time to do that, as far as I know. That would be really helpful. And I know the videos are super long and like annoying because I talk so much. But one thing I'll say to everybody is this: one of the reasons that I keep the whiteboard like so big and prominent on the screen is I think it helps. You can scroll through the video. You just watch the whiteboard and see where the whiteboard is at to find the place you're looking for, to find the question. Like, you know, if you're just anxiously waiting for question 4, just scroll until question 4 appears on the whiteboard is the best thing I can say. But I know the videos are like a lot. And I have to think, I mean, one day I'd love to make it a project to edit them down and all that stuff. And if anybody wants to do that as a research project or something, please let me know, or for money or something. But yeah, but anyway, okay. All right, all that said, I'd like to ultimately get back to homework 1B, but I think I first have to keep my promise, for good or for bad. I have to keep my promise of going back and quickly running through homework 1A and showing you what the purpose of it was. So let's do this. So we're going to turn to homework 1A, which again is obviously an informal homework. It's sort of cutesy, but there is a purpose to it that I want you to know. Again, all this physics ends up looking very mathy, but I'm sure many of you have noticed in science in many classes, in a way, the hardest part about all the math in these science classes is not the math itself. It's knowing how to set up the math, right? How to set up questions. So part of the purpose of this UnthingyThings thing is to give you the background for this course so that you know, so you have context of like what it is that we're looking for, what we're trying to do in this course, which may help you better dive into problems as they emerge. So, okay. So UnthingyThings. I'm just going to change that. All right. I want to change the view of the screen. UnthingyThings. Well, we're talking. All right. I'm going to change the view of the screen for a second. Okay. We're talking about this, right? Is it on your? Yeah, we're talking about this, right? So it asks you to clear your desk of everything except for 2 arbitrary objects. Let's say that my 2 arbitrary objects are, well, actually, that's interesting. Let's say my 2 arbitrary objects are like this and this, like a pencil and a, whatever this thing is, a radio. And one object I'm calling thing 1 and one object I'm calling thing 2. Okay, now this gets a little, thing 1, I'm defining, whenever I say from here on in thing 1, I mean the point at the center of thing one. And whenever I say thing two from now on, I mean the point at the center of it. Now, I'm also assuming, this is going to get into a little bit of issues. I am assuming here, not just the point at the center of the object, but a point at the center. Right now, I'm sort of deliberately picking two objects that seem to have mass going throughout them. I'm assuming right now, for the sake of clarity, that at the center of each of these objects is some stuff, like some plastic or whatever. Things can get a little bit more dicey if one of these objects were like a donut or a cup or something, as some of you very cleverly picked that, and it very smart if you did, like I see your point. But for the moment, let's just assume that both these objects are sort of solid throughout. And so when I talk about thing one, I'm referring to the point at the center of thing one. And when I say thing two, I'm talking about the point at the center of thing two. Okay. And let's assume that I'm trying to be intuitive and take the sort of most common sense interpretation of these questions, at least for the moment, or at least the most self-consistent interpretation of these questions as I go through. So I'm also kind of assuming that space and time I can in my mind picture as being composed of a bunch of little points, little pixels, right? Like something is at this point in space, or it's at this point in space, and it's happening right now, or it's happening right now. That's my picture in my mind. That's a general physics picture. All right, so now it's giving me 5 tasks. The sheet is giving me 5 tasks that I'm supposed to attempt to do. And my job is to assess which of these tasks is basically possible, which would probably mean easy, or so difficult that it's basically impossible. And I'm not trying to overthink any of this. And more important, whatever interpretation, I mean, obviously people can interpret my words different ways and all that. But one key standard is whatever interpretation I deploy for the words of question 1, I want to use that same interpretation for all the words in question 2, 3, 4, and 5. Like I don't want to shift interpretations midway. I don't think that would be fair to anybody. So, okay. So, and the goal is not to overthink. The goal is to let this thing do thinking for me and then come to a conclusion. So I'm going to say, I looked at all of your homeworks. Right. First of all, I was looking to make sure that you did actually address these. All you had to do was write down a couple of words like possible, possible, impossible, or whatever. But I did want you to address this. And if you didn't, maybe I didn't give you all the points. And frankly, I was intrigued to notice that a lot of people had a lot of different answers. Now, we could have a really fascinating discussion about this right now. We're not going to, because we're trying to make tracks. But there were a lot of, but suffice to say, if you think what I'm about to go over right now is obvious or like a waste of time, I want to start by saying, well, apparently it's not, because people gave answers that were all over the map to these 5. Okay, so, but I will cut to the chase and tell you what I think the most reasonable answers are to these 5. I think number 1 is possible. And some people said it wasn't, and I'm not shaming them, but let's get it straight. I think you can have the center of these 2 objects. I don't know if you can see in the video. You can have the center of these 2 objects at 2 different points in space at 1 point in time, as I'm doing right now. Well, you can't, I hope you can see, right? That's a demonstration. We're not trying to overthink it, but you can have 2 of these objects at 2 points in space at 1 point in time, at like so. I think number 1 is possible. If you think it's impossible, and just because you interpreted the question differently or you had a different thing in mind, if now you're like, oh, duh, that's what he meant, then fine, great, we're together, you still got all the points, don't worry about it. But if you're thinking, wait, no, I don't think that's not what that means, then put in the chat, like I'm open to other, if you think there's something legitimately like upsetting about this, I'm all ears. But if it was just a miscommunication, then let's leave it at that. And I think the answer to number 1 is it's possible. Again, don't worry about why I'm asking this for the moment. Trust me, I'm going somewhere with this. But I think the answer to number 1 is it's possible. Number 2, I just flipped 2 words in the question. But I am asking, so it's a more awkward question now, number 2. I flipped the word space and time. I maintain I'm now asking a different question. It's not nonsense. It is more awkward than the first, perhaps. Maybe it's more unusual, but it's not nonsense. We're asking something different now. But I think the answer to this one is also possible. what would I do to demonstrate that? I would do something like this. I would go, right? Well, you can't really see. Can you see? I would go, right? And then I go, right? Like here's this object, or here's the center of this at this point in space. And then a little bit later, at another point in time, here's this object at the old point in space, right? Like, and again, I'm just trying to be reasonable here. Now, in the past, I've heard people say things like, well, wait, but didn't the Earth rotate when you just did that? So aren't you slightly off the second time? Like, I'm not saying whether, I mean, could I nail it necessarily exactly right by all factors in the universe? Maybe not. Maybe what I just did, I kind of did it wrong. But definitely, even by accident, if I tried to do it wrong, if you want to incorporate the Earth's rotation or something, if I tried to do it slightly wrong, then I would by accident do it slightly right. Like it is, in my mind, it is clearly possible for something to be here and then later on something else to be there, right? Then, so I think number 2 is possible. Again, don't worry about why I'm asking this for the moment. Just worry about whether you agree. But notice this, I think number 1 is possible. Number 2 is possible. They're both possible, but they're possible with different demonstrations. So they're not asking the same thing. It's 2 different things. One is 2 different points in space at one point in time. The second one is 2 different points in time at one point in space. Now, evidently, these objects can accomplish both of those goals, I think. Again, you are welcome. I'd love to hear disagreement or questions if you want them, but in the interest, but that's what I think so far. Now, so I think 1 and 2 are possible. Number 3, place thing number 1 and thing number 2 at the same point in space at the same point in time. In other words, have these 2 at one point in space at one point in time. Now that I do not think is possible. Like I can have these 2 things touch each other. Yeah, I can do that. But I can't have the center of this at a point in space where the center of the other one is, right? I can't, they bang off each other. And it's not just because I'm not trying hard enough, right? Like, let's be clear. Oh, sorry. Yeah.
Which point are we on?
Which one are we on? We're on number 3.
Okay.
Hold on, just Evelyn's raising. I want to get you to Christopher, but since Evelyn or Evie is raising her hand, let me get her. I'll just back up for a second and say, I'm on number 3. I think 1 and 2 are both possible. I'm asserting now, and I'm open to discussion for sure, but I'm asserting, I think if you interpret the words the same way throughout, I think 3 is certainly with these objects, I think it's impossible, but maybe, but let's hear. Okay, Evelyn, first of all.
So I used, same thing as Dennis said in chat. I used a pencil and a ring, and like I put the pencil through the ring so their center points are in the same place. So I think it's possible.
Okay. Oh, and I didn't see the chat. I'm sorry. Wait. So first of all, that's brilliant. I do want to address that. I mean, I don't know if it's brilliant. That's really smart. I'm totally down. I even remember that you and a couple other people said that. Wait, let me just see if that's what's in the chat too. Okay. And thank you, Dennis. Now I see you in the chat also. Now, I'll address this right now. This is what, and I'm not criticizing. I think that's brilliant. But I sort of did remember at the beginning, I sort of did see it coming when I said, right now, let's assume that both of the objects are solid throughout. Like at the beginning, I was on purpose saying, like, let's assume one of them is not a donut or a cup or something like that. At first, I was just saying that just to first, like, take the easy, like the most simple, straightforward example, mine, I think we all agree it can't be done with these 2 things. But now I do agree with Evelyn. I'm not blowing it off. I think it is brilliant what Evelyn is saying, and who else? And Dennis said. And they certainly, in terms of points or grades, I mean, not only do they get all the points, but also, yes, I noticed that I think that's really smart. I mean, I think it really shows a cool interpretation of the question. But now let's all just pause and realize what it means, though, that they did that. Of course, they're right. Yes, yes. If you pick, I can't even get this off anymore. Thank God my wife can't take her ring off either, because we've both gotten fat because anyway, whatever. I can't take this ring off, but like my finger and my ring, yes, demonstrates what Evelyn and Dennis are saying. But now notice, they had to come up with, in order to make 3 possible, they had to come up with 2 objects, one of which doesn't have stuff at its center. Like the reason their technique works, the reason their very smart technique works, is that one of their objects they picked has a center of mass that has no mass, right? Now, that doesn't prove that they did anything wrong or anything like that. But the reason they had to do that is because they know in the back of their minds, and I know, that if there had been stuff If the ring hadn't been a ring, if it had been a disc, then of course the pencil couldn't fit there. The pencil, the center of the pencil, in other words, could fit at the same point in space, at the same point in time, as the center of the ring, as long as the center of the ring had no thing there, right? As long as it was a ring. So that what that shows me, again, it means that they're being very smart about the question. It doesn't mean they've misunderstood the question or anything like that. But what it shows me is that we were all actually on the same page of realizing that two amounts of thing, two bits of stuff, whether you want to call it matter or material or mass or particles, which of course we get to at the end of the sheet, somehow you can't actually have two bits of stuff at the same point in space, at the same point in time, right? The fact that one of your two things would have to be a ring for this to work, again, it shows they do understand the question. It doesn't mean they got the question wrong, but it brings out what the question's trying to bring out, which is that if we're actually talking about stuff, if we're talking about thing, material, which I will ultimately define by the end of the sheet, two pieces of material evidently can't be in the same place at the same time. They can be in two spaces at one time. They can be at two times at one space. But apparently two bits of material can't be at one space at one time. I think, wait, I'm looking at the chat. I think I see the chat is lighting up. Hold on. Wait, sorry. Right. So again, back into the chat again, and I hope this is clear. I'm not being sarcastic and I'm not being cute. Like I totally think what Evelyn did and Dennis did is super smart and super like full credit. But I think it's another way of bringing out ultimately a similar observation, which is somehow stuff doesn't want to share space and time with other stuff, like whatever I mean by stuff. So wait, so I think, and maybe one of those, maybe Dennis or Evelyn, either in private chat or public chat, just tell me if nobody hates anybody or something like that. But okay, I'm looking at the private chat now. Hold on. Okay, hold on. I'm just responding to direct chat here. Hold on. Wait. Oh yeah. Okay. Oh wait. Oh, and then okay. In the public chat, Samantha Davis is right. I mean, to Samantha's question, is there the important distinction between a whole object like a ring and the concept of mass matter itself? Yeah, just so that I'm not trying to leave anybody in the dark. Where I'm going with this ultimately is I'm trying to get at really what is meant by a particle in the end. Like that's why that's the last question on the sheet. Okay, so right, I totally agree. You can put a pencil inside of a ring, or you could put an ice cube inside of a cup, and like that's why a cup is cool, and so forth. But the reason that works is because a cup is a cup. Like the reason we invented cups or whatever is that we intuitively know that we can't put ice cubes or liquids even into blocks. In fact, I'm gonna go one step further. We even know that when we put an ice cube into a drink, right? We even know that when we put an ice cube into a drink, we know the liquid level rises, right? Water displacement, you all know about from 7th grade or whatever, right? Well, we're used to it, but what does that mean? It means that even when it comes to a liquid, liquid does not want to share space with solid. If there's amount of liquid here taking up a certain volume, a certain space, and then you put a solid in, like whether it floats or sinks, doesn't matter. The liquid spreads out around it and then rises up because the liquid will not share ultimately space with that solid. And I'm going to go even a step further now. You blow into a balloon and you blow up the balloon, right? Oh, weird. Okay, fine. Oh, I love, I'm going to open up a portal for that. I'm totally going to open up. Remind me, you'll notice more portals have been opened up. Totally going to open up a portal for anybody that says anything that I seem to be slightly disagreeing with or whatever. If they then put in a cute joke or cute happy observation afterwards so that I know nobody hates anybody, it's so freaking helpful to my humanity. I'm totally hoping. I mean, I'm inferring it means nobody hates anybody, which is great. Like, anyway. So yes, thank you. I'm trying to read your minds. But what I'm reading is everybody hates everybody. No, but think about this for a second. And this does blow my mind when I think about it. If you blow into a balloon, what do? You blow up the balloon, right? You blow into a balloon and the latex or the rubber, whatever, it starts expanding, right? Well, so what? What does that mean? Like, duh. Well, it means that even the air that just came out of your mouth, which is like not barely tangible, barely seeable, visible, barely massable, like right? But evidently material, like the gas that just the oxygen, which is a gas that just came, or the carbon dioxide that just came out of your mouth, which is a gas. How did it expand the balloon? It shoved the latex, the rubber, out of the way because solid doesn't even want to or isn't even willing to share space with something as abstract as a gas. I.e., when you were in third grade and you learned about the states of matter, the phases of matter, solid, liquid, gas, like I swear I was 30 when it's 30 years old, when it suddenly hit me like, oh, the states of matter, solid, liquid, gas. Oh, gas is matter. Gas is material. Like as ethereal as it is, or as, whatever, flimsy as it is, it's matter. It shoves solids out of the way. Like that's how windmills work or whatever, right? So what we're getting at ultimately here is, what does it mean to be matter, to be material? It means, in part, so far at step 3, evidently, it means unwilling to share space with your neighbors. Matter doesn't share, will not occupy the same point in space at the same point in time as other matter, even if that matter is a gas, right? Okay, so I'm just saying that. I don't know why. I mean, I do, but I don't care why. I'm just saying. So in my world, right, if the two objects are solid, if it's not a ring and a donut and a then I believe the answers so far are 1, possible, 2, possible, 3, impossible, then 4. Now, 4 is interesting because honestly, a lot of people said a lot of different things about 4. I'll just assert again to keep moving here. I will assert that 4, I believe, is possible. And in fact, I think it could be demonstrated 2 distinct ways. 4 is, possible. A lot of people said it was impossible, which, by the way, again, shows me that you are taking the question seriously. Like, unless you're like literally throwing darts at a board. Like, I think 4 is very awkward English. I can see a lot of reasons why someone would say it's impossible. So there's no shame in it, but I think it's possible because it says put thing 1. So I'm just looking at thing 1 now, whatever. I'm just looking at thing 1 of the things now. And it says, have it occupy 2 different points in time at 1 point in space. So, okay, one way I could do that. So 1 point in space, right? You can reverse the order. It's still the same thing. 1 point in space at 2 points in time. I can go, for example, like this. I can go, right? That would be an example. It was here, and then sometime later, oh, okay. Everybody's home. We're about to be interrupted by Pokemon trainer himself. But I don't know how though. Could have sworn. Anyway, something might be wrong, and I apologize in advance if this might be a real interruption, and I beg your indulgence if we're about to find out because people are home unusually early. But okay, if I go like this and then and then I go like this, something is occupying 1 point in space at 2 different points in time, right? Now, there's another way I could do it too that I'm sure some of you either are thinking or were thinking, and it's also legitimate. I could just go like this, right? I mean, it's here now, and it's also here later. That's two. I mean, it's also there at all the points in between, but I mean, that's fine. So I think 4 is possible. There's something in the chat, and also I may pause for a second, but wait. Thank you. Wait, I'm not sure quite how to take that, but thank you, I think. Wait, pardon me. I'm going to pause for a second just to make sure everything's okay, because this is a little surprising. Hold on. Pardon me for a second. Okay, we will be interrupted, but it'll just be because my son is a freak, not because anything is wrong. Those of you who have children totally understand where I'm coming from here. Okay. To this day, if I call either of my parents and they pick up the phone, I always say, hi, it's not an emergency. I always say that or hi, I'm good. Now, can I have money or whatever? No, I don't do that. Okay. Number 5 now, to get straight to the point. To get straight to the point, and many of you, I think many of you put this down. I think we're on the same page on this one. Maybe it's the least controversial. I think 5 is impossible. You cannot have one object. You can't have the center of one object. You can't have one defining mass point of one object occupy 2 different space points at one time point. Like, again, I understand that this is an extended object and the entirety of it is occupying many space points. No dispute there. But if there's one point that I'm using to define the whole thing, that one point is not, cannot be in 2 places. Hello, sir. Good to see you. Okay, welcome. Okay, so right now at this moment, what I think, and you can stop me again, my summary of just the observations is that I believe tasks 3 and 5 are impossible. Now, who cares? Why am I doing this?
How are they impossible?
They're
That's the big question.
my son just said, how are they impossible? That's the big question. Yes, that is the big question. I think okay. I gather that. Well, yes. Okay, we'll see. Oh, they know. Yes, I'm sure you can. Okay, here's what I think. Actually, wait, I'm going to switch boards now. The purpose in doing these possible, impossible things. Dude, wait. You could in an hour and 45 minutes. Thank you. Hold on. Pardon me, everybody. I'm switching, and I really do need to teach now. Wait, sorry. Pardon me. Felix, I need to teach.
Last beat my dog.
Okay. What I'm saying is tasks 3 and 5 are impossible for things that are really thingy, right? Like for stuff, for objects that are discrete, i.e. divisible, material, identifiable, like there's that object there, or that's not, like by identifiable, you could even say bounded if you like. Like a can is identifiable in the sense that it has a boundary, it has an outside, and some things are inside the can and then some things are not in the can, and you can make that distinction, right? So any object that is thingy, that is really tangible, massive, material, countable, bounded in this sense, these objects that we all intuitively think of really as objects, i.e. like stuff that's not in the center of a ring. So again, this is all affirming, and I want to be clear about this, affirming what Evelyn very cleverly said, and Dennis very cleverly said, and I think maybe Christopher, I'm not sure, like once you have a thing that's thingy, it can't be in 2 points in space at one point in time, and it can't share 1 point in space at one point in time with another thingy thing, right? Now, here's my point. is that the actual scientific term for such thingy things, of course, for things that are so particular as that, is particle, right? In other words, tasks 3 and 5 are impossible for what we know in physics and science for particles. But let me be more clear now. And again, of course, in a way, everybody knew this before we started. I mean, in a way, you know this, but you might not have known that it mattered or that it would lead to anything. I'm here to tell you it does. Tasks 3 and 5 are impossible for particles. But here's 2 twists on that. Number one, it's not a double equal sign. It's a triple equal sign. This is not just something that we notice about particles. This is actually what it means to be a particle. In the last question of the sheet where I say, hey, what is a particle? I got a lot of good answers from a lot of you. I know sometimes I marked them up and sometimes I didn't, but I read them. And a lot of you said, I mean, people said all kinds of things. And a lot of people said things, especially based on the rhythm of the whole sheet. A lot of people said things like a particle is something that exists in space and time, or occupies space and time, or something like that, or can be measured in space and time. And also a lot of people said a particle is a really small thing that exists in space and time. In truth, in physics, a particle doesn't actually have to be small to be a particle. Technically speaking, a planet is a particle. An electron is a particle as well. It's a subatomic particle. But a planet is a particle, a star is a particle. A particle is, yes, it is something that occupies space and time, yes. But anything that occupies space and time in a measurable, analyzable, predictable way, anything that occupies space and time is the province of physics. Lots of things occupy space and time. We're going to get to that in a second. A particle is something that occupies space and time in a very specific way. The specific way is this. A particle is something that occupies space and time, but cannot perform task 3 or task 5. In other words, what I'm saying is, it's not just that we notice that tasks 3 and task 5 are impossible for particles. We don't just notice that. A particle is, by definition, ultimately, is something that cannot do task 3 or 5. Oh, and I see the chat. I'll get to the chat in 1 second. And I'm still not done. There's still a reason I'm saying all this, but I'm going to get the chat in 1 second. So what I'm saying so far, and I'm going to look at the chat, and I'm saying so far, what a particle is, what a thingy thing is. Yes, a thingy thing has all these, it's tangible, it's countable, it's material, it's identifiable. But the essence of what it really means to be a thing, what it means to be a particular bit of material in the world of space and time, what it means to be a particular bit of material is to not be capable of occupying 2 time points and 1 space point. I'm sorry, to be not capable of occupying 2 space points at 1 time point, and to not be capable of co-occupying 1 space point at 1 time point with another such particle. That's what it means to be a particle. Now, I'm about to look at the chat, but let me tell you, if still you're like, okay, but you're just running in circles. Wait, I'm totally about to look at the chat. I see exciting things are happening in the chat. Let me just like blurt part of this out and then I'll look, because again, I think people are with me. But if by any chance you're thinking in your mind like, okay, I get it, but you're running in circles, like, all right, so you're saying like stuff can't be in the same place at the same time, but now you're saying like, that's why we call it stuff. So like, so what? Like we knew all this already. I'm going to tell you right now, after I look at I'm going to tell you, none of this would matter to me at all. None of this would be interesting. except that I'm going to assert to you that there are things in the world, in physics that do occupy space and time, but aren't particles. Like, all of this is important to know because there's a whole realm of things that are real and are subject to science, physics, but are not thingy in this way. Like, none of this would matter except for the fact that this does not cover the whole world. This is only part of the world, is particles. That's why I'm making this important distinction. A particle is something that cannot be in two places at once, but there are things in physics that can be in two places at once, or there are things in physics that can share one place at once with another thing. And that's what we need to get to in a moment. But first, I'm going to look at the chat. Hold on. Oh, woohoo! Sorry, I'm reading the chat out of order, but I see things in the chat that are ordered like spot on. So wait, okay. Okay, wait. So, okay. So wait, so first of all, okay, there's great things in the chat. Okay, I'm just gonna go in order, okay? Bear with me. So first of all, there's something in the chat that says, that apologizes, said, sorry if I already answered this, but how are we doing? How are we going to do the 5-step method again for homework 2? So I appreciate the apology, and it's a fair question. So the truth is, I did actually answer it because it is a legitimate question. I do want you to do the 5-step method for homework 2. There is a way of drawing diagrams and all of that. And so I totally appreciate that you're asking. I'm going to say, I actually spent, please rewatch the video at your leisure, and you've got like 5 days to do it. If you rerun this video, once it's posted tonight, you'll see that at the whole beginning of the class, I kind of broke that down into detail. So I'm not saying this in a scolding way, but like, yeah, it's a fair question, but I do expect you to do the 5-step method, and I do try to explain it at the beginning of this video. So please watch it tonight, and maybe tell me privately if you hear me, if that's okay. But yeah, and again, that's to everybody. I want to encourage you all, like, you're allowed to ask something that I mean, hopefully I won't redo every answer, but at least I can tell you whether I did it or not. Not everybody catches everything at all times. Like, I totally know that. Okay, so that's that. Now there's also something in the direct chat. I'll get to the public chat in a second, but I'm totally down with what's in the public chat. So someone asked in the private chat, so can a thing also be a particle? I think that's what it can. So a thing can also be a particle. Here's my direct answer to that. Particle is the real scientific word, right? And like, thing is not like really scientific. But what I'm saying ultimately is that there's two types of things in this world. There are two types of, I mean, maybe there's many, but there's at least two types of things in this world. There are things that are very thingy, that really seem like things, that seem material and solid and massive. And ultimately, those things are called particles. The kind of things that really seem obviously like things. Now, I would say the kind of things that are material, countable, discrete, divisible, etc., are things. But what do I really mean by that? I mean the kind of things that cannot be in two places at once and cannot share one place at once with another thing. Those things are called particles. What I want to get at now, and what's happening in the public chat, what I want to get at now is, those are not the only kind of things that exist actually in the real scientific world. There's a whole set of other things that are things, but are very unthingy. That's obviously not the scientific word. The scientific word is, there's a whole bunch of things that are not particles. I will give you my word for that in a minute, but I will now.
Do waves count?
Okay, so waves are absolutely an example. Yes, are an example of an unthingy thing. Waves are one big example of something that absolutely truly exists. Or let me be more specific. Waves are a perfect example of something that occupies space and time in a measurable, analyzable, predictable way, i.e., therefore, waves are within the province of not only science, but specifically physics, right? Waves are an example of entities that absolutely exist in the world and are studied by physics. However, so correct, yes. However, I would call them unthingy, or I would say, whoa, they're not particles, because waves, two waves can occupy the same space at the same time. Right now, and I'm seeing the chat is going crazy. I'm psyched with everything in the chat. And thank you, by the way, the person in the chat who said, understood, Professor, thank you for explaining. That totally counts as closing a path. I hope you can double dip that. Like, that's not just your participation for the day, but also you also put the same screenshot in the portal that says closing a path. Like, and I hope that's clear to people. And sidebar to anybody, if you've put in anything in participation, and for the 5 points, and I wrote at the bottom, double dip, I'm saying, please take that exact same entry. And there's at least one more portal somewhere that you can put that same entry into the other portal and get more points for. And I'm telling you to do it because you earn the points, but you won't get the points unless you do that. Okay, so yes, so thank you for the person who's like saying that I explained. Now, before I get to some of the intense things that are in the chat, what I'm trying to say to everybody is waves are one example of an unthingy thing, of an entity that isn't a particle. And the reason I'm having this whole discussion with you right now, before I say more about waves or I say more about other examples, well, actually, let's do this. Wait.
I wonder if volumes that occupy masses count, like say like an air mass, hot air mass versus cold air mass.
Well, okay, but remember what we were saying before, that's very clever. But I think gases, even though they seem very hard to touch, gases really actually
Still particles.
Yeah, I think so. Yeah, because they move each other out of the way. Like, it's harder to see that, but they really don't. The particles of gases really don't share space, and that's why, like, they expand containers, and they move pistons in cars and so forth. But right. So gases really, truly, ultimately are particles, I think. But like you said before, I think you said, yes, you said in the and other people are saying in the chat, water waves, or actually, let me be more orderly about this. Waves on a string, because you're going to see that in the lab next, waves on a string, like as in on a one-dimensional string, waves on 2D water, and then most commonly, maybe importantly, you might argue, sound waves. Now, there's going to be more examples in a second, but all these waves, and I'm going to get back to the chat in a second. Let me just start by saying waves absolutely are an example of something that's totally real, but totally not a particle, right? And the reason I'm doing all this and saying all this is because if it's not already clear, this list of things that we're about to generate, this list of things that are unthingy, of things that are part of science, but are not particles, this is the point of this course, okay? The reason we have Physics 203 and then Physics 204, the reason is that the principles and patterns, i.e. the equations, the laws, the definitions, are the same in both classes. The laws of physics, the goal of studying how things move through space and time is physics. That's the same in both classes. But the reason physics starts subdividing into one course and then another course, and the reason that the math gets more and more abstract, or the math becomes more and more important or something, is that we don't change the rules of the game. The game is things moving through space and time. But we start looking at things that are increasingly abstract. The point of Physics 204 is that everything ultimately that we study in this class, and we have to transition, we have to get there. And the first homework is meant to be the transition from particle physics, from looking at a mass sitting on a spring going back and forth. We are setting all that up to finally get to the deeper math of that, so that we could put a bunch of oscillating objects together in the next couple of homeworks, or just so you understand the course. We start with our old physics, our laws that govern how particles move back and forth in space, entities that cannot share space and time with each other. And we look at oscillation deeply enough. We look at the mathematics of oscillation deeply enough so that we can ultimately take a bunch of oscillators, put them next to each other, an oscillator here, an oscillator here, an oscillator here, and trigger them so that what starts rippling through the set of oscillators is suddenly something that we would call a wave pulse, or other words for it. And a wave pulse is real, it's physical, it's predictable and mathematical, but it ain't material, right? We are ultimately here in Physics 204 to apply the principles and patterns of physics law to immaterial entities, non-particles. The purpose of this course, I guess, just to cut to the chase, and then I'll go back to the, is to build up enough knowledge of oscillations to be able to understand first waves, which we and then I'll just give you the examples right now to save a little time, to then go from waves to fields, which are also immaterial but real, i.e. gravitational fields and electrostatic fields, to electrical currents. Again, currents are real. They run our house. You know, I mean, they run your car. Electrical currents run everything. They ain't material. They're not massive. They're whatever. You see where I'm going? To finally get from E currents to magnetic fields and ultimately to what's known as electromagnetic radiation, otherwise known as light. The ultimate goal of this course is to get to a deep mathematical understanding of the nature of light, which is the most unthingy thing of all unthingy things. The purpose of this course and why the math gets heavier in this course than the last one is we're doing the same physics, but we're applying it to a study of unthingy things, of non-particle entities. What's the larger, and I know I'm just trying to set this all up. I will go back to the chat again, but just so that we have this laid out. And at first we're studying the oscillation of one mass on one spring. That's still technically old physics, but partly we're doing it to review old concepts and partly to transition because we're going to build our immaterial entities they wouldn't be real. All these non-particles wouldn't be real. They wouldn't be part of the real world if they weren't somehow tethered to or generated by material entities in the material world. But we are ultimately here to study the immaterial entities occupying the material world. And one larger word to encompass all these things, whether you want to call them waves or fields or radiations or energies or whatever, the one word that I would use to encompass all this stuff that we are studying in Physics 204, like the informal word would be unthingy things, but that's not. But what all this is information. Physics, here's a sentence you could write down that I'm not going to write down, but if you want to write this down, screenshot it for extra points in the new portal. I'm saying, and then I will stop and I'll look in the chat and then we'll move back to the other homework. I'm saying Physics 203, we studied the trajectories of particles. We studied how a particle moves, how an individual, countable, discrete particle moves from here to there. Whether the particle was a rubber ball or was a car or was a rocket ship or was a planet, we were looking at Physics 203. We studied the trajectories of particles. Physics 204, ultimately, we study the propagation of information. What does propagation mean? It means flow. Physics 204 is about the flow of information. What is information? Well, any of these things like sound, light, electricity, math. But what is information? Information is stuff that matters in the world, but isn't matter. Information is stuff that occupies space and time, but not in a particular fashion. Okay, so this is why we did that exercise. It's to understand from here on in the goal. we're studying this mass on the spring going back and forth, but it's like boring. I know it's boring to me, but we're studying it to get enough mathematics of oscillation so that we can then put together a bunch of oscillations together and create a propagation. And from there on in, all this course is about immaterial propagations. Okay, now, so that's the point. That's the point. Then we're going to, after I look at the chat, which I really appreciate, like a lot of things I have in the chat, it's great. Then I will turn our attention back to 1B and to the math appertaining thereunto. Okay, okay, so I answered that. So waves was a great answer. I saw the word waves all over the chat, both in public and in direct chat. Great, yes, waves. Okay, so then people are asking in the chat, aren't photons considered both? Yeah, so that's great, fair. Obviously, you've been, many of you have been in science for a long time, and hopefully many of you are very interested in science. So yes, ultimately, if you study anything in quantum mechanics, in modern physics, we ultimately find out there's a way of looking at things so that we ultimately understand them as both. Particularly photons are ultimately understood as both. But I gotta say, if I'm not careful, I could go on about that forever. I mean, that's a fascinating topic, of course. I'm not saying I'd be right in everything I say, but I mean, I would happily discuss it with you forever. Let me say two things about it right now, though. Number one, that is interesting. But I can also tell you that the reason that's interesting, the reason it's interesting that anybody ever says that a photon can be considered both, the reason we find that interesting is because it's mind-blowing, because it makes no sense. Like fundamentally, see, I don't want to go. I will talk a lot about that as we get closer and closer to light toward the end of the course. I will say a lot more about that toward the end of the course, I promise. But that's a big surprise. Let me put it that way. That discovery in the 20th century, to discover that somehow, some way, light seems to behave like both, is a very, very big surprise. And we will address it in this course. But we don't want to skip steps. If you really want to, and I'm not saying it's wrong, but I'm saying if you want to appreciate the depth of that surprise and you want to appreciate why it's significant, you first have to appreciate that it's a surprise, because by definition, that makes no sense. A particle is a thing, and a wave is a bunch of particles moving in a certain way. A wave is not a particle. A wave is not a thing. So something either is a thing or it's not a thing. It doesn't make any sense to say that a thing, like you can say that a thing can be two types at the same time. A thing can be red and it can be tall. That's fine. That's like not a contradiction. A thing can be the color red and it can also be the height called tall. But a thing can't be literally all over it, red and not red at the same time. It either is red, or it's either all red or it's not all red, right? Or I'm either here or I'm not here. That's like logic, right? I can't be here and not here. Similarly, something can either exist as a thing or it doesn't exist as a thing. Waves are not things in the definitions I'm presenting you right now. So a thing is either exists or it doesn't exist, which is why for centuries, people wanted to know whether light was made of particles or waves. What they were really asking, they weren't asking is light have this feature or that? If you've ever heard of this debate over centuries, it's a very legitimate, fascinating debate. People went back and forth over actually millennia as to whether the motion of light consisted of the motion of particles or waves. But you have to realize that the reason that debate is so important is that's just a way of saying, is light made up of little bits or isn't it? It doesn't make any sense to say that it both is made of little bits and it's not. A brick house is either made of bricks, or if it's not a brick house. So anyway, but yes, you're right. In modern terms, we've encountered all these surprises and weird revelations. I'll get to them at the end of the course. But for the moment, what I would say is in order to appreciate, but we don't need any of that to do the math of this course or to do the stuff. So to keep things organized and to keep our brain moving in order, I would say, set that aside, that idea about photons and being considered both. It's not wrong, but I'm saying it will confuse things in the course at this stage. Okay. But fascinating. I'm glad you know. Okay, so I'm still looking through the chat. Right. And so also someone's asking about Schrodinger's cat. in the chat, which is great. I'm glad you all know about that. And I know you've seen references to this maybe in chemistry and I'm all for it. I don't want to blow it off at all. I love it. I live for it. Things like that is why I became a physics major in the first place when I was in college. It's all fantastic, but I just want to go in order and get there. So, and I think you'll appreciate things like Schrodinger's cat even more when you see why it's such a paradox. And the first paradox is what we're saying right here is a thing. To be a thing, to be a particle in physics, in classical physics, in every way that we understood physics until, say, 1905, well, even, yeah, till 1905, even beyond, what to be a thing is to be in one place at one time by yourself. That's what it means to be a thing. Okay, I'm still looking at the, so right, like what Evelyn put in the chat, I'm down, like sound waves, light waves, sometimes when they're not particles, right, fair enough. Right, those are the kinds of things we're ultimately in this course. This course is ultimately about waves on a string, sound waves, and gravitational and electrical fields, electrical currents, magnetic fields, and electromagnetic radiation. I mean, that's what the course is like on paper about. But the thread through all of that is these are all immaterial entities that we're applying old physics principles in order to understand. So great. Okay. Okay. So yes, oh God, how long ago did this person? All right. Someone in the direct chat very politely said, thank you for your explanation of 1A. Do you mind if we go over 1B soon? Great question. It was 11 minutes ago that someone asked that. I feel a little bit bad, but yes, that's totally my goal now. Yes. But thank you for politely like keeping me on track. So yes, I'm just going to finish the chat and go there. Oh, wait. Oh, now someone's asking me, my handwriting is, okay. I always appreciate when people do that. So sorry to interrupt, but what does line 2 say? Line 2. Oh, yeah. You totally can't read that. What line 2 of the blue here says, oh my God, yeah, that's completely illegible. What it's trying to say is waves on 2D water or surface of some liquid. I'm trying to say, like the first thing that we study in the lab, like I think you're going to study in your very next lab on Monday, is waves going back and forth on a one-dimensional string. But then you can extrapolate from that. We don't do a lot of problem, but you can extrapolate from that waves going around and interfering with each other on the two-dimensional surface of something like a pond. So I'm just making that, so I'm just saying waves on a 1D string is an example, then waves on like a 2D surface, maybe of water is another example. It turns out, by the way, that light is waves in 3D, which makes it even more interesting, but we'll get to that. Okay. Thank you. Thank you, Sarah, for what you say there to thank in the chat. Great. I appreciate it. Okay. They are everything. Oh, everything is thermodynamics. Well, there's some everything is everything. I mean, thermodynamics. Yeah. I mean, everything's thermodynamics in a way. Yes. Okay. Thank you. Okay. Oh, and whoever said in direct chat at 5:38, thank you so much for something else that I answered about direct chat. Thank you for saying that, and definitely submit that to the portal. And I hope you all see also anything you submit to the portals, they don't have to be public. They can be, the private chat is great and it works much better for some people. Okay, but I think that is the chat. So I think you guys are doing great. We have, I think, an hour and 5 minutes. Cool. We can now go to homework 1B. Again, I know it's all a little bit nonlinear, but hopefully you see we're going to get wherever we're trying to go. So now homework 1B. Okay, back to homework 1B. Okay. Okay. Now I'm going to try to move a little faster now. Wait a minute, just here. I'm going to ask you. Okay. Yeah. All right. I think so. We did question 4 yesterday. I'm going to do question 5. Is very similar to question 4. Hopefully this explanation will be a lot tighter. Again, here's my diagram, just so we all know what I'm talking about. You don't have to keep doing this, but just what I'm talking about. Oh, I'm on step. So I believe the question for question 5 was at or when V equals 3 meters per second. What is X, right? That's a question for that. I mean, stop me if I'm wrong, I believe it is. So now we did all this, we spent all this time yesterday establishing all these things about work and energy and potential energy. So now they're all established. So I'm going to use the principle that we established. The principle from yesterday is that oh, why am I writing in red? I'm sorry. That's going to confuse me. Okay. The principle is E at X equals 0 equals E at X equals X naught, right? The principle here is that total mechanical energy is conserved for the spring because all the forces doing work on the mass are conservative forces, right? All that was established last, and you can even say C question 4, right? So energy is conserved, but here what I want to be clear about now, to say that energy is conserved from one spot to the next means, so I'm still in step 3 here, all the kinetic plus all the potential at one spot is the same as all the kinetic plus all the potential at another spot, right? This is still step 3 continued. So that means, okay, 1/2 mv squared plus 1/2 kx squared at one spot equals all the 1/2 mv squared plus all the 1/2 kx squared at another spot. And what are these two spots? Always, when you're doing energy conservation, one spot is a spot where you have all the information, and the other spot is a spot where you're looking for the information. What's the information you're looking for? Well, if you know what the two spots are, the information we're talking about is instantaneous speed. So always, this is a spot where you know the speed compared to a spot where you're solving for the speed. Or in this case, I guess it's vice versa. You know the two speeds, and you're looking for one of the spots. So it's just the reversal of the old question. Pardon me, there's okay. So now I could start filling it again. Remember, notice my tendency, what I'm trying to teach you is postpone actual number crunching for as long as you possibly can. So first of all, I can factor out 1/2 of E, but just notice again, please. I guess this is my big cautionary tale to everybody, because by the time we get to question 5, honestly, this is a place where a lot of people got wrong answers, like, or didn't know what to do. So please notice the thing that you don't do in question 5. You don't say 1/2 mv squared equals 1/2 kx squared. If in 4, in 4, it looks like that's what you did. So if you're really not understanding what a dp is, you could accidentally just lift that from the end of your question 4. You could think, or if you look online in a sort of haphazard way, you could think that that's an equation, 1/2 mv squared equals 1/2 kx squared, but it isn't. It's a result of a particular circumstance. The equation here is total energy over here equals total energy over there. So that's what I'm dealing with. So first of all, I can factor out a 1/2 from both sides and divide both sides by 1/2. So, okay, I can, I'll say, I'm sorry. So now I'm in step 4. Like, I've set up everything. So now I'm in step 4, particular application and work. Like, now I'm starting to get particular. I'm starting to plug and chug, as you say. So first of all, I'm going to divide both sides by 1/2, right? And now, if I'm not careful, I might think, wait, but it's the same crap on both sides. Like, can't you just like subtract mv squared from both sides and subtract kx squared from both sides, and like, don't you end up with like nothing equals nothing? Well, no, not if you start plugging in, not if you're careful and realize, okay, at x equals x naught, at x equals x naught, certainly v equals 0, right? We crossed this, the same thing happened in question 4 yesterday. At x equals x naught, at the amplitude position, the initial position, the initial velocity was 0, sure. At x equals x naught, x wasn't 0. I don't cross that out. What is x? X is x naught, right? So I'll say, in other words, so I'm plugging in now, but I'm not plugging in a number yet. I'm just plugging that value. Now I go to the other side. Now, yes, now this is where I'm careful again. At x, oh, sorry, I'm sorry. Oh, this is an error. Wait, no, there's nothing in the chat. No one caught this error. Oh my God, I'm making an error. No one caught it. I'm now going to pretend that I was making the error to see if you were paying attention, and you weren't. No, the error is this. We're not comparing x equals x naught to x equals 0. That's what we did yesterday. We're comparing x equals x naught to x, the unknown x that we're solving for. So I'm going to, so this shouldn't say x equals 0. That is a mistake that I made. Let me just correct it on the other page. Hold on. Oh no, that's, well, yeah. Now wait, I apologize. I mean, I'm not messing with you. That is a legitimate mistake, but because I just changed something, let me just pause for a second. Can you just raise an electronic hand if you just caught the correction that I just made? Awesome. That's 2, 3, 4, 6, 7, 8, 9, 10, 12. Awesome. Okay. I think that's a quorum. All right. Thank you, guys. I'm not going to mention it. Thank you. It's only telling me Samantha and Dante. Okay. Thank you. And I don't, okay, great. So you catch it. All right. So the x is the x that I'm solving for. It's not 0, right? I mean, it's not 0. And thank you. And you can put your hands down now. Thank you. So it's not 0. It's the x that I'm solving for. But also v is not 0. Right? This is not like yesterday where we can cross out a term on either side. That's really the purpose of this question. It's not just to repeat the same procedure and bore you. It's to show you that that v is not 0. We're not talking about the amplitude position. And also v is not 3.87. We're not talking about the equilibrium position. We're talking about the 3 that was given in the problem, right? And x is not 0. X is, we don't know, we're looking for. But now I'm at the point where I see everything is a known here, except for the x that I'm solving for. So and I just put that 3, I even that 3 in my own personal work, I wouldn't even put that 3 in because I don't like that number sitting there, but I'm just doing it to clarify to you guys. That's what we mean by v, the v that was given as 3 in the problem. So now I'm just going to do algebra before I start crunching numbers. I'm solving for x, right? I'm not solving for x naught. X naught is a given constant. I'm solving for x. So I'm going to rearrange. I'm going to say like, okay, kx naught, I'm going to subtract like, m3 squared from both sides. That looks a little clunky, but there it is. I'm looking for x. So I'm going to divide both sides by k, and I'm going to square root. So we have this. Right now, I know that we're now at a point where a lot of you would have already plugged in the numbers and then rearranged. It's the minute you ever get to a point like this where it seems a little awkward to you to rearrange before you plug in the numbers, I encourage you to try it. Get used to it now while it's a little bit awkward, because ultimately it will serve you better to be plugging in numbers at the last possible minute. You want to get used to this kind of algebra. First of all, you want to get used to it. Second of all, if I keep the algebra like this, please note every single one of these lines, this last line, I mean, I'm not done yet, but this last line on the sheet here, this is a result. Like this would be true. Now, this could be an equation that you could now publish, or you could have at the front of a textbook and memorize. Like this is now a physics result that's true in all cases described like this case. And the more you get used to seeing things like this, the more you could even just, before you go any further, before you put the numbers in, you could start checking units in your mind and seeing if this is right or wrong. Like you want to get used to thinking in terms of general physics, not just particular arithmetic. But anyway, we have that. But I know it's an adjustment for many of us. Because we have that, I'm just going to recopy it on the next page. We're almost done. X equals square root . Okay, now I've isolated X. X is what I'm solving for. It also helps to remind me what's the point of all this. So now I can literally plug in. So it's 200. X naught was 0.15. I probably should put the units in, but it's going to get really messy. M is 0.3. 3 squared is 9. K is still 200. Also notice, please, for some of you this is obvious, but some of you notice I cannot cancel out the K's. I can't cancel out the K's because there's only a K in the first term in the numerator. If there were a K in also the second term of the numerator, then I could factor it out. Then I could cancel them out. I'm just right, but there isn't a K in the second term, so I cannot cancel out those 200s or those K's. Right? And you can, again, in the chat, if you're uncomfortable with that, let me know, but it's true. Now, also, this gets back to something a bunch of people were asking yesterday. I believe the actual question asks, where is X such that the instantaneous speed of the particle is 3 meters per second? I believe it says 3. I mean, I believe it says speed. Correct me if that's wrong. But since it says speed, that could mean that the particle could be going in either direction. It means that the velocity could be +3 or the velocity could be -3. So truth, right? Stop me if that's not true, but I think it says you're correct. Oh, great. Thank you. Wait, I'm sorry. I'm correct. Awesome. Could you screenshot that and make it hugely big? Just the you are correct part. No, okay. No, thank you, Allison. Okay. So, all right. So if that's correct, thank you. So if that's correct, and this gets to what some people, maybe Allison was one of them, I can't remember, but some people yesterday were like pointing out to be careful. That means there's really 2 different positions. Whatever I solve for you, there's 2 different places. There's one on the right side when the thing is going in a particular direction, and then there's one on the other side of equilibrium when it's going in the other direction. So truthfully, really, I'm looking for both of these routes, right? And again, this is where it's physics, not math. Like, it's not just that I'm following math rules. I'm thinking about the physics of the physics question. But yeah, I think strictly speaking, it's plus or minus whatever all this nonsense is. And so it's going to be 200 times 0.15 squared, I believe, is 0.0225, I believe. And 9 times 0.3 would be 2.7, I believe. And that's all over 200. And then what you get after you do all that in the calculator, you will get, I believe, I mean, you have to round, I would say, to go to 3 significant digits. We could talk about that if you don't have to be freakish about significant digits in I shouldn't use that word. The rule of thumb with the lecture recitation part of the class, like lab is different, but in the lecture recitation, in the homeworks and exams, the basic rule of significant digits is include in your answer, basically include the maximum number of significant digits that was presented in any part of the problem. That's actually the opposite of what you do in lab if you're following me. But basically in the problem, you were given numbers like 200 newtons per meter. And then you were also given a number like 0.15 meter. But if we were being strict and careful, we would have said 0.150 meters. You were given, it went to the level of precision of 200. So just as a rule of thumb, and I don't get crazy about this on exams or anything, but as a rule of thumb, your answer should include 3 significant digits, since that's what sort of was the most that was provided in the problem, but it shouldn't provide any more. So I'm rounding. And that's why it's an approximate equal sign, since I chopped off digits. But I think this is the answer. Okay, sorry. Okay, I'm looking at the direct chat now, but I think that's the answer. Oh, sorry. And I will look in the chat, but I think. Okay. But I believe that's the answer. Oh, I'll say one more thing, and then I'm going to stop and look in the chat. Note that answer. It's enough work here that there's no way that's not a guessable answer. Like it's a weird enough number. It's not like, oh, duh. Obviously, I saw that coming right from the start. I mean, you have to do the calculation, but it is. But you can look at that answer and know that it's reasonable, in the sense that, let's remember, and I will look in the chat. Remember, this thing started off with a velocity of 0. And then it was moving in and gaining speed until it got all the way to equilibrium. I'm sorry, let me start again. It started off at 0.15 meters. from equilibrium. It started off at 15 centimeters from equilibrium, and then is moving in until it gets all the way to a speed of 3.87. And we're looking for the place where it had a speed of 3. So we're looking for a place that's between 0.15 and 0. So it's a good thing we got a number that is bigger than 0, but smaller than 0.15. That doesn't prove that our number is right. But if we had gotten something bigger than 0.15, that would prove that our number would be wrong, right? So this is at least, this seems reasonable. And it is correct, I believe. Now, let me look. But again, I'm going to look at chat. You could say, what if I did it a different way? I mean, there is more one way to do this. If you did it a different way, if it looks a little different, but you basically used energy and you got this answer, fine. If you did it a different way and got a different answer, like 0.113 or something like that, then I think it's because you made a mistake. I think you said 1/2 mv squared equals 1/2 kx squared, which isn't true. If you did it a different way and you did something like x equals a omega squared or something like that, then probably on your homework, if I saw that, I probably wrote www. And I want to say, I'm not saying that's wrong, but I'm saying, whoa, where's that coming from? I hope you understand what that is, if that's what you did. If you do, and you could show you did, Quark bless America. But I don't know anything about a omega squared or anything like that yet at this point in my brain. So I think this is the most straightforward way to do it. All right, I'm going to look in the chat now. Okay. Oh, yes. I'm so sorry. Okay. This is a great question in the direct chat. And I almost want to use this person's name just to give this person credit, but I won't. But I hope this person. So someone wrote in the direct chat, Professor Walters always asked us to include a reference diagram, including which way is positive and which way is negative. Should we include this for this diagram? Yes. I'm so glad that she emphasized that. That's so huge. And it is so, I'm so ashamed of myself that somehow I've not been emphasizing that. It's been slipping my mind. Shame on me. That is hugely important. And credit to her and credit to you, direct chat person, for bringing that up. Next time, maybe you'll even go public. Yeah, no, that is really a thing. And maybe I've just done this problem so many times. It's really irresponsible of me that I didn't include that, honestly. I mean, I live for that. You'll see, yes. All I can say is yes. And good, you are a good person. I'm literally, and I'm going to see Professor Walters soon. You know, she's having I'm not giving it, you know, she's having a baby. I'm not giving anything. Anyway, I'm going to her. Anyway, I'm going to tell her that you learned that so well that you even corrected me on it. I'm so proud of her and you. Yes, it is. I should have done that. And I will do that in the future. It's totally my failure that I didn't. And I will say, for the purpose of this problem, had I remembered to do that, I would have said plus was to the direction to the right, because I think that we've been treating the 0.15 as a positive number this whole time. So yes, I should have said to the right is positive, to the left is negative, and that's totally my bad. And I'll totally open up a portal just for that. Okay, so yeah. Oh, and so yes, now other direct chat person, this is awesome. Yes, I believe that both these answers, the positive and negative, for this question, because of the way this physics question was phrased, because Allison confirmed that it asked at what position is the speed 3, I believe there are 2 answers. Yeah, like the math technically reveals 2 answers, and both of them are physically meaningful. So yes. Now, if you left off one in a homework, are you like not going to get an A? No, I mean, I might note it if I'm going through slowly enough, and if it were on an exam and it was exactly this question and you left off one, I might take off 1 point by the time we get to an exam. I might. And if it ended up being really important in further questions, then it'd become important. But so yes, technically we want both those answers. Okay, I'm going to look at the chat again. But good question, both of you. Christopher forgot that was a thing. Well, Professor Walters forgot that Christopher was a thing. No, she didn't. She talks about him all the time. Okay. Yeah, no, you're making me so happy. I'm so glad that Professor Walters constantly reminded you guys of that. I'm so proud of all of you. And I'm not kidding that she and I will talk about this. And I'm embarrassed that I didn't do it. I can retire now. Okay, no, that's great. It really, really is important. Okay. Isn't she awesome? Okay. Okay. Okay, and we'll talk more about her as we all get to know each other better, but yes, okay. Okay, so that's that one. 6:01, we've got 45 minutes. Okay. All right, I'm gonna keep, I know, so, all right, let's just say, I'm gonna catch my breath for like if you need to take like 4 minutes to go get a drink or balance your fluids, otherwise do it. Let's take like I'm like a 4-minute break. I'm just gonna, a 4-minute break, just if you want to run and get a cup of coffee or whatever. And I'm gonna catch my breath, and I'm gonna set up the next board, but like 4 minutes, and then we'll keep going with this. Thank you. You're welcome. Okay, I'm gonna start again with chat. Great question. Okay, so I'm gonna start again. Welcome back, everybody. If you're still coming in, I get it. So I'm starting slowly. There's a great question in the direct chat. which is, can we still turn in revised version of the homework, even though I went over it? Yes. Totally legitimate question. I totally this may be unusual. It's not true in every class, but yes, yes. But let me put this a different way. Yes. Yeah, okay. Yeah. No, it's serious. But I know that's weird. But yes, if you could, because if nothing else, it shows you're getting something out of class. If you're understanding now, again, to everybody, once you turn something in, it's totally fine to have gotten help in understanding it from anywhere and everywhere, including Khan Academy, including your colleagues, including my old videos, including class. You can get help in understanding things from everywhere and use that help to make revisions and turn those revisions in after the original deadline. Absolutely. And I have reasons for that. The one thing is and you don't have to footnote or you don't have to say I got this. I mean, sometimes if you want to say I got this from class, just to be more extra honest, you can, but the point isn't that you have to cite anything. The point is that by the time you're writing it down, you're only writing down things that you understand, right? And this is not just to the direct chat person, I'm saying this to everybody. You can and should use class to help your understanding of things that you didn't understand before, but use class to help your understanding. So then by the time you write it down, you're writing it your way. Your diagrams, your extra thought bubbles on the side of English, your commentary, your steps. Your goal in all of these homeworks is to convince me that you know what you're doing. And I mean that very seriously to all of you. Your goal is to show that you're not just copying stuff, that you've brought stuff from the outside, filtered it through your personal understanding, and are now giving it back to me through your understanding. Now, how do you do that? The best way, and I can already tell with homeworks, believe me, the best people, because you all have different styles. And the more each one of you, the more confident a person is, and the more they or even maybe are bored because they really feel like they understand or whatever, the more you feel in command of the material, the more your personal style accidentally comes out. For example, people they write the algebra down, but the more they understand, the more they're putting English to the side, explaining each step, or the more you understand, the more you break it down into smaller and smaller steps. Have you noticed that I talk a lot? Have you noticed that I talk a lot? Have you noticed that it takes me a long time to get to the point, but yet somehow I always seem to be somewhere near it? Have you noticed that I have a lot to say about each one of these seemingly simple steps? That's because I have a lot to say about each one of these seemingly simple steps, because there's a lot in my mind about each one of these seemingly simple steps. Each one of these steps I could, if I'm not careful, break down into smaller and smaller and smaller steps. And for some of you, that's a benefit that I do that. For some of you, it drives you crazy, but it's a little bit hard to deny. I don't think any one of you would say that I'm copying all this from somewhere else. Right? I mean, I don't, right? Obviously, I'm saying all this stuff because there's so much in my mind about each one of these steps. That's where you want to be. You want to be that person who has so much understanding of each step that you could give a lot of mini steps and a lot of side commentary and a lot of cute original drawings and blah, blah, blah. Why am I saying all this right now? Because that's what you're going to do on the exams. All of these homeworks are practice. Oh, yeah. Oh, I see the direct chat. Yeah, although I sort of did. Okay, yeah. Yes, thank you. And that counts as your, sorry. Yes, direct chat. Thank you. That counts as a reminder to, what I meant was remind me to talk about WWW, which I think I kind of did earlier in the recording of this. But yes, hopefully I am going to get to the last question shortly. So yes, thank you. Totally. Okay, no, okay, Mike, we're all good. We're all good. All right, so back to everybody. I know I'm on another one of my little tears here, but look, we're going to have an exam at the end of next week, as we've already established. If you don't already know, you probably do already know. If the exam is take home, the exam is take home, and you have a couple nights to do it. And when I say it's take home, do I mean then I'm expecting to somehow take home and enforce some time window with webcams and that you can't open your notes or you can't? No, I'm not crazy. Am I crazy? Well, yes, okay, I am. But like, I mean, am I going to take someone who's on a diet and put a huge cake in front of them and say, don't eat it? Like, that's obnoxious. I'm not going to give you a take-home exam and then say you can't go on the web. Like, you have to be a non-human for 3 days. Like, how could I right? So no. So just to get to the chase, your take-home exam is going to be open universe. And I've done this a million times. That may be unusual to some of you. Some of you right now be thinking, well, that's a gift. Sort of, but sort of not. Your exam, you're going to be able to use any resources you want in order to complete the exam, including your friends. Because secretly, that's my fantasy, that you help each other get smarter in this class. So you're going to have any resources you want, certainly including all my old lectures, any other person's lectures, blah, 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 all your notes. It's open universe, the exam. So what, and I will have given you a practice exam before with certain solutions, not all. So what the heck am I testing you on? Like, what is to stop? What's the deal with that? The deal is your job on the exam is to go to town and show me not the right answers, because I'll already know that you already know that I know that you already have the correct answers. That's not the test. The test is to show me that you understand deeply why the correct answers are the correct answers. That's why we do the 5-step method. That's why we're walking through all these homeworks the way we're walking through them. And yes, we'll get faster and faster. But I'm telling you all right now, I know I sound angry. I'm not angry. I'm just excited. Just, yes, you have ample opportunities to keep revising your homeworks based on what we did in class. But every time you revise, you're trying to get in the habit of learning what it means to show, to prove. We're here to do physics proofs. You're trying to prove that the results are true from first principles, and you're trying to prove that you understand the proof. So the more original you can be, the more commentary you can provide, the more like English over here, algebra over here, arrows down there, different colors, big formatting. That's what you're doing. You're trying to present a mental command of the language of physics, almost as though it were a poster board at a research presentation. Okay, I'm going to go back to the topic, but I just want to clear, that was a great question someone asked, like, can we revise homeworks even after you've already gone over there? Yes, you totally can, because they're all practice for the big game, which is the exams, which by the time you get there, you want to be able to know how not to just give answers, but to show me where the answers came from. So yes. Okay, sorry. Okay, so back to the program. Okay, to speed along, question 6, I think, well, you could stop me if you don't know. I think most people knew that the answer to question 6 was 15 centimeters on the other side. And like yes, I should have produced a diagram right from the start, that the whole situation was like that. Right, assuming to the right is positive and to the left is negative, I think the answer is negative 1.15. And if you want to show your work for that, I'm telling you right now, I'm going to move on, but the GDP for that is energy conservation. If you set up the energy conservation again and solve for do the exact same thing you did in question 5, where you solved for a place where the speed was 3, what you're trying to do here is you're trying to solve for all the places where V is 0, right? You already know one of the places is 0.15. But if you set up the math and solve for the 2 roots, the 2 places where V is 0, you will see that the 2 roots are 0.15 and negative 0.15. It's energy conservation. It's gonna, if it has a certain amount of potential energy when it has 0 kinetic energy, it's gonna have the same amount of potential energy the other time it has 0 kinetic energy. So yes, I think intuitively most of us can guess that, hopefully most of us guess that this is probably the right answer, but it absolutely is mathematically derivable from the same principle that you used in question 4 and 5, which is energy conservation. Okay, but unless there's a question, oh, sorry, yeah.
So I have a question.
Yes.
You said we can mathematically derive an answer. But what if in that moment when you were like doing the exam, you took a logical approach without using numbers like conservation? You're like, okay, cool. No kinetic energy means no speed. So can we use that approach instead of working with like an equation or something like that?
Very, very fair question. Absolutely good question. And the answer is absolutely yes. You can use the language of English instead of the language of symbols of mathematics. You can absolutely use the language of English instead of the language of math But as long as you're accomplishing the same goal, which is deriving, justifying, proving the answer, you could say energy is conserved. Like you could say the thing that I just like said very quickly a second ago, that energy is conserved. Therefore, the total amount of potential energy when the kinetic is zero must be the total amount of potential the other time the kinetic is zero, and therefore, absolutely, you could do it in English, but it still has to be an explanation. What you can't do is just say because you see it intuitively in your mind. You can't do what some people, you can't say common sense says. It may be sense and it might be common, but if it's sensible and it's common, you could identify it for me. But yes, absolutely, it doesn't have to be equations. Equations are just a shorthand for English, absolutely. And I love, and on that note, on Christopher's note, again, not to go on out, honestly, when it's exam time, I'm not just saying that's okay. I'm not just being polite to Christopher and saying like, yeah, he can get away with that. No, the more English, the better. Honestly, the more English, the better. The more English you can use to explain the mathematics, absolutely the better. And if you can do English instead of mathematics a lot, yeah, that will really show that you understand, because you'll almost necessarily use different words from the words that I would use. English is good. It just turns out that math saves time sometimes. But yes, no, all of you, the more I could see English or pictures, a lot of you are this is where the diagram thing comes in. Think of all of these things, the things that seem like pains in the butt, what they really are just different routes, paths available to achievement. Like some of you draw really well, clearly far better than I do. So go to town with the drawings. I'm kind of just saying, anyway, you get my point. So yes to Christopher. Okay, so that's that. So that's question 6. Okay, then question 7. I know we all want to, believe me, I want to get to question 9 also, and I will. Even if we don't finish today, I definitely want to get there. Question 7, I don't remember what it is. Question 7, I think it's how many trips does it make? Yeah, so this too, here, I'm just going to cut to the chase here too. The principle again is energy conservation. The principle again, and you can write it in English or whatever, but the principle again is energy conservation. And what that leads to, however you want to explain it, is if there's no friction, I mean, if it's energy conservation, it will make infinite indistinguishable cycles. Now, again, you could say, well, that's not perfectly realistic. Well, it's not perfectly realistic for something to perfectly conserve energy. That answer, infinity, is just as realistic as any of the numbers that we've gotten to this point, if you know what I'm saying. So that, like, there's no energy is conserved means it will, there's no reason it will keep stopping at 0.15 or negative 0.15 on either side. There's the equation will keep generating 0.15s and negative 0.15s. I think you all get it. That the answer is because of energy conservation, it'll go on forever. Now 8 gets a little bit more interesting, a little bit, and then leads us to 9. Question 8. So it's asking about, so it's just asking. Let's remember now, question 8. Okay, that's positive, that's negative. But let's be very clear that question 8 is entirely only concerned with the first quarter cycle of this thing's mode. Like it's going to say, oh, it's going to go back and forth forever. We just established in question 7. So it's going to oscillate forever. That's called oscillation, going back and forth and back and forth. I should say, yeah, in fact, let's just make that clear. Sorry. Where we say it's going to go on forever, the word for that, and I know you, I'm sure picked up on this in lab, but this is oscillation. And by oscillation, what we really mean is cyclical periodic motion, a motion that repeats over and over through time and repeats over and over in a predictable patterned or what we call periodic fashion. Okay, so from here on in, what we're establishing is if you let this thing go, if energy is conserved, if there's not a lot of friction or whatnot, this thing is going to not just move in one direction, it's going to oscillate. It's going to repeatedly, cyclically go back and forth indefinitely. Okay. Now, question 8 is concerned with the first quarter of the first cycle of this oscillation, just from the initial position to the equilibrium position, no further, right? A full cycle from here on in, let's be clear, you might want to write this in your notes, even though I'm not going to. A cycle means a round trip, a closed path. A cycle is, by definition, there and back. So there would be a half cycle. Midway, like to the other amplitude point, would be a half cycle. To the equilibrium position is a quarter cycle. That's all we're concerned about in this question. And we're asking about speed. Like, is it going up or going down or staying the same? And then we're asking about acceleration. Going up, staying the same, or going down. And then we're asking about the derivative of acceleration, which the English word for that is jerk. The English word for the guy at the front of the Zoom class is jerk. But no, it is. So in other words, we're talking about the magnitude of dx dt, the magnitude of d2x dt squared, and the magnitude of d3x dt cubed, right? The first derivative of position with respect to time, magnitude. The second derivative of position with respect to time. The third derivative of position with respect to time. Okay. We want to answer these questions. Now, by the time you get to and here too in the homework, I'd like some kind of explanation for your answers. I need some kind of reasoning. A lot of people get the first one right, maybe the second one right. A lot of people have different things to say about the third one. The third one's where it gets thought-provoking. You might never have thought about third derivative before. So one hint for how to approach this or how to approach that third one is let's back up. Even though the question just asked about first derivative, second derivative, third derivative, maybe there's a pattern here that could be established. If we want to see the pattern convincingly, why don't we back up? Why don't we reframe the question and back up and ask ourselves first, or let's break the question down into an easier question. And let's first ask, what about x itself? What about the function? I'm saying the question didn't ask that, but it would be easier. Did I just lose? Uh-oh, what's happening? Okay, so it's not what? Okay. I'm saying it would be, whenever a question is hard, it's helpful to break it down into a simpler version of the question. So I'm going to ask myself first, what about the position? Okay, we're just asking about whether each of these functions is going up or going down, just in magnitude, right? It's a little confusing. Like, we're not asking to incorporate pluses or minus signs into our answers here. So the position, it starts at position 0.15, at positive 0.15, right? And it goes to position 0. So straight up, the position is going from positive 0.15 to 0. I say the position is going down. I'm not trying to trick anybody, but I'm trying to establish something. I think the position is going down, right? Now let's look at the speed. Okay, at the beginning, at x naught, the speed right here is 0, but we know that the speed right here at equilibrium is approximately 3.87 meters. So the speed is going from 0 to positive 3.87 meters. So I think the speed is going up. The thing is speeding up. That also doesn't surprise me, because the mass is accelerating, right? Like it's got a force on it from the spring, a force pulling to the left. So it's accelerating to the left, so it's speeding up from 0 to 3. It's accelerating positively. It's speeding up its speed is going up. You could stop me again in the chat if I'm saying. Now, the acceleration. Okay, now let's be careful. Someone actually raised a couple of interesting observations about this 2 days ago. Let's be careful about the acceleration now. Like, it's very easy if you're not careful, or back in your early days of physics 203, it's very easy to confuse speed with acceleration. It's very easy to think that when things are speeding up, then they're accelerating up, which is not the case necessarily, right? In fact, a lot of physics really is about probing the deep distinction or relationship between speed and acceleration, or velocity and acceleration. What I'm getting at here is this thing is accelerating. It is speeding up as it moves from the beginning to the equilibrium. But its rate of acceleration, I assert, is going down, not up, right? Let's be clear about that. Like, and a lot of you got that right. I'm not saying that. I think most of you got that right, but let's just be clear. It's speeding up. It is accelerating in the first quarter of the cycle. It's speeding up, but the rate at which it's speeding up is going down. And that is not a contradiction, right? And what I specifically mean, why I'm saying that, and you can please tell me in the direct chat if you're uncomfortable with that, or please think about it for a minute, because it should be a little bit of a bumpy idea. I'm not saying you shouldn't accept it, but I am saying it's getting faster and faster and faster, but the rate at which it's getting faster and faster and faster is going down. It's gaining speed at a lesser and lesser rate. How do I know? Why am I saying that? Well, number one, F equals ma. It's being, like, the bigger the force, the bigger the acceleration. And this thing is being pulled less and less as it gets closer to the equilibrium, right? That's the whole point of elasticity. It's being pulled really hard while it's way out here. It really doesn't want to be way out here. F equals negative kx. The force is proportional to the displacement from equilibrium. So it's being pulled really hard here. As it gets closer to equilibrium, the spring is pulling less and less until it gets all the way to the equilibrium, and the spring isn't pulling it at all. It's totally happy now. Like we said 2 days ago, by the time it gets to equilibrium, its acceleration is nothing. It's zero. At the beginning, the acceleration was 100 meters per second squared. Now you could say, wait, I thought it was negative 100. Yes, it is negative 100. That just means it's pointing in. The magnitude of the acceleration is enormous at the beginning. The magnitude is 100 meters per second squared, and that magnitude is going down and down and down all the way until it's zero at the center. So the speed is going up, i.e. there is acceleration, but the magnitude of that acceleration is going down. I want you to be clear. Think about that for a minute. Make sure it's clear in your mind. It's an interesting observation. It's true. And I see there's at least one thing in the chat. But please make sure you're cool with that before I go on. Okay, wait, I'm looking. Oh, this is good. What's in the direct chat? Wait. Oh. Okay. One second. Okay. Okay. Okay, so that's that. Now, that's that. So now this next question, which is the harder question. I mean, it's the question we might not have ever considered in 203. What about the rate of change of the rate of change of position with respect to time? What about, i.e., the third derivative, i.e., the jerk, not this jerk, that jerk? Right? What about that? Like, how are we even possibly supposed to know? We've never even considered this before. Like, is there an equation for that? What? Well, the first thing I would say is we have a pattern here. We definitely have a pattern here. And if I have no other information to go on, I would consider whether I have some reason to trust the pattern. And put a different way, do I have any reason to believe that this pattern is suddenly going to stop? In other words, kind of the essence of Newton's first law, kind of the essence of physics is that things stay the same if they're left alone, right? Objects maintain constant velocity. Objects don't change the way they're moving unless they are forced to, unless there's an external or identifiable influence on them to. So I'm saying sort of metaphorically or figuratively, I could sort of extend that. I'm saying I see a pattern here in the derivatives. I don't have a guarantee that this pattern will go on forever, but if I'm going to say that suddenly the pattern is going to stop at the third derivative level, I'm saying that somehow the third derivative should be special, that something special is happening at the third derivative level. And I can't think of anything special. That is, I don't know any equation, and neither do you, about third derivatives. So I'm going to suggest right now that if there's anything to this pattern at all, and I think there is, it seems to me that based on this pattern, the next derivative would go up. And so on and so on and so on forever. There's another way. Wait, I'm just looking at the time. Do I want to argue? I can argue this further. I think you don't want me to, though. That's the answer. Okay, there's more that could be said about that, but I know many of us, including me, are anxious to at least get to question 9, start setting it up. So we've got 12 minutes. If you have any issues about that, you could make a note of it and ask me on Monday. I'm happy to go back to it, but I think that's the answer based on the pattern. I think the next derivative must be going. So the third derivative must be increasing. And I think that pattern goes on forever. And what I think is, what I'm getting at is this type of motion, F equals negative kx, seems very simple. It's just force is directly proportional to position. But there's something very deep going on here. This is the first type of, it's simple, but it's not easy. This motion going back and forth, what I'm ultimately saying is for something to continuously go back and forth, for its position to change continuously, its velocity must change continuously. For its velocity to change continuously, its acceleration must change continuously. For its acceleration to change, the next derivative must change. Evidently, this motion, even though it seems simple, it's just back and forth, evidently this motion contains within it a property known as infinite differentiability. All the rates of change are happening here. And if you really think about it, they must be. For any one rate of change to be flopping back and forth, for any switch to be going back and forth, the switch on the switch must be going back and forth. That's what we're really saying here. Anyway.
Wait, I'm sorry. I know you want to go to the next one. I have a question. Couldn't we just look at the derivative of acceleration as the rate of change of velocity? We know that acceleration is the rate of change of velocity. Couldn't we just use our answer from the previous, saying that, hey, we figured out that the velocity increases and acceleration is the rate of change of velocity? Couldn't we use that derivative to determine the derivative of acceleration, how it would work, using how velocity works?
Wait, I think I know. I'm not sure I totally understand. And it's true, I'm a little concerned. Wait, this may be a very deep question. I'm not sure. But if you knew the function, if you could write out the function and take the derivatives, then yes, absolutely. But we haven't yet. I don't know that we don't have a function yet to take.
Because what I did, I did acceleration equals kx over m, and seeing that k and m are constant, when I found the derivative, I put k and m out, and then I ended up with dx over dt, and you know the dx over dt is velocity, so I ended up getting dA over dt equals kx, well, k over mv, you know, or kv over m. And v in this case is velocity. So I use the behavior of velocity to determine the derivative of acceleration.
That's great. Sorry. Yes, that's awesome. Yes, you could do that. And I may want to say more about that next week, but yeah, that's awesome. Yeah, that totally works. And maybe I'll do it that way next year. Yes, that's great. I thought you meant something else, but that's great. That's great. And thank you. And I am, wait. Okay, wait. I do want to move on. Well, okay, so someone's putting in the chat, why does jerk increase? And I do appreciate your honesty. I'm going to say quickly now, I may get back to this on Monday because I would like to at least set up the last question because everybody's been waiting for 2 days. But to the person in the direct chat who's saying, I'm a little lost, why does jerk increase? My fast answer, my simplest answer is because of a pattern, because of that pattern. Because I have no reason to believe that that pattern won't continue since the function went down and the first derivative went up and then the second derivative went down. I'm assuming that pattern is going to go on forever. That's my quick answer. But I will say more about, but that's not a proof. And one good proof kind of is what Christopher just said. If you want to replay the tape later, it works. I like it. Please forgive me. I'm going to go on now just so we have 8 minutes. I want to set up at least the next one. But my fast answer to why the jerk, and maybe tell me in the direct chat if this is okay for you for right now. My fast answer is it continues the pattern of those derivatives. But okay, I know we have 8. Okay, I just want to, so I apologize to everybody, but I'm going to get to question 9 here. Okay, question 9. Okay, of course, we're not going to finish it today. I will say that I saw a lot of things in a lot of homeworks where a lot of people did a lot of right things for this last question, way more than I've ever seen in the past at this stage of the semester. And at first I was like, what is going on here? Are people cheating or what? And then I realized for a lot of you got a lot of good knowledge, partly from the lab, I think. And also some of you watched past videos. And that's fantastic. That's actually that's starting to work finally, these stupid videos. Like if you got any information from lab that helped you do the last question or from past videos, like Quark Bless America, that's totally not cheating. That's great. But you didn't have to do that. And not everybody did that. And I still have a lot of things to say about question 9. So I'm not going to finish it now. But I'm going to start setting it up with the knowledge that some of you seem already comfortable with it. But this is going to get us into everything. And we'll pick up with this, in 7 minutes, we'll stop and we're going to pick up from here on Monday. And then we'll go to homework 2, blah, blah, blah. But the question 9, the diagram C above. Okay, diagram C above. Question 9 is technically it's at t equals 1. What is x, right? But really, what am I really asking here then? I'm really asking, what is x as a function of t, right? We are trying in question 9 to see how position depends on time. In other words, 1 is just an arbitrary example. We need some kind of equation where you could plug 1 in for t and get out x. Our goal here is to get that equation, that function that in a way I was just alluding to with Christopher a moment ago. That is really the goal here. Okay. And as the homework says, you can't use x equal, we want something like x equals 1 half at squared plus v naught t, something like that. But that one's not right because a is not constant. So any constant acceleration equation won't work. So what is our function? Well, the way to get it, we're just going to set this up right now. What's our GDP? What do we, but I will say this now. This is where things get hard, this last question. A lot of you did a great job of taking stuff from lab or from past videos or whatever. That's all great. But a lot of us, if we just first looked at this, did not know what to do right away. And that's totally fine. This is where the 5-step method really starts to come into play. Because any of you some of you wrote things like something, they write like F equals MA, and then they would write, I'm lost. And that's honest, that's fine. I'm lost, I don't know what to do here. But here's where you do the method. If you don't know what to do, start by writing down not just the information of the problem, but general definitions and principles that we've been using throughout the problem. They will trigger more information. In other words, we write down F equals MA, that's a GDP, right? And we write down F equals negative kx, just like we were doing in the earlier steps. Like this, I'm on step 3. GDP. This is where if you don't know what to do, you write down things that are true and then try to make them relevant rather than the other way around. So here's my GDP. So what am I going to do with this? I'm now going to go, okay, so now I'm going to go into step 4, PAW. I'm going to put these two things together and say, okay, since the only force, I'm doing this fast, I will back up on this on Monday. But if the only force here is the spring force, then negative kx equals ma, right? Oh, and sorry, and here's one other GDP that I should have written a second ago. Sorry, that's not wrong, but I'm just, sorry. One other GDP that I almost forgot that just sort of came up in the last question, not coincidentally. Another GDP is that the definition of acceleration, the definition of instantaneous acceleration is the second derivative of position with respect to time. That is what acceleration, instantaneous acceleration, means by definition. Right now, that's a GDP. That's a general definition of. So let me put these three things together here now. And again, I'll back up over this on Monday. But if I put those three things together, now I can say, fine, negative. So this is now step 4. So negative kx equals ma, right? But a is d2x dt squared. So negative x equals m d2x dt squared, right? In other words, we have this. Now, let me pause for a second. This is not an answer yet. This is not an answer, and we have to do a lot to think about this in the next couple of days. But what we have here, notice we have an equation that only has x's and t's in, or that the only variables in this equation are x and t. And that is what we're looking for. Like, this is the dependent variable. And this is the independent variable. And of course, this is the dependent variable. Everything else in there is a constant. It might as well be like K and M are just like numbers. So we have all the information that we're looking for. We have X related to T. It's just not expressed in a form that we want. We have to unpack this. This thing is not giving us X as a function of T. It's giving us some kind of derivative of X with respect to T as a function of X. This is called a differential equation. I'm not expecting you to have taken a class called that yet. I'm not, but I am expecting you to stay with me and follow how we deal with this in physics. This is a differential equation. What this is saying, and I know I have 2 minutes left. I'm just going to do like one more step and we're going to leave it at that for now. But what this is saying is remember our goal is to find X as a function of T. We are looking for some kind of X, which when you differentiate it twice with respect to time, like we're looking for an X such that when you take the derivative of it, you get itself back times some constant, K over M, times a -1. That's what we're looking for. That's what this says. It says we're looking for some kind of X, which when you differentiate it twice, you get back itself times a constant times a negative sign. What the heck is that? Well, to cut to the chase, just we have something, and many of you people knew this in your work, just to cut to the chase now, but I swear I'm going to back up on this and say it more slowly on Monday. But to cut to the chase, the kind of function that comes to my mind, if I look at the data from your lab, if I look at the graph that would express something going back and forth in time, if time were my x-axis and x were my y-axis, right? If I think of graphs and if I think of functions that I know, which when you differentiate them twice, you get back themselves with a negative sign. One such function that comes to my mind is cosine, right? Because the derivative of cosine is negative sine and the derivative of negative sine is negative cosine. So I'm guessing. And especially because it seems like such a good guess, because when I think of something going back and forth smoothly in time, I think of cosines or sines. Why am I saying cosine? Because because this object didn't start at 0,0. It wasn't at equilibrium at time zero. Okay, so I know you'll have to go. So I'm just going to say, here's my guess. I'm going to guess x equals x naught times cosine of k over mt. And that's just a guess. But if you differentiate that twice, you'll see you get back negative k over m. Oh, sorry, square root. That's a guess. I'm going to expand on that on Monday. But you can prove that that guess is right by just taking two derivatives of it. And if you take two derivatives of it, you'll get negative k over m times that. So that's my guess. And if I plug in 1 for t and 200 for k and 0.3 for m, I'll get that x equals 0.116 meters. But that was very fast. I'm going to expand on that and slow that down starting Monday. I just wanted to, give you the over. Anyway, you've all been very, very patient. Start on homework 2. We will just talk more about that on Monday. Then we'll go to homework 2. I promise. But keep going with whatever you're doing. You're lovely. I will hang out for 2 minutes for whatever questions. But thank you very much. I'm going to stop the recording also. But I'm here if you want to ask.
Hi, Professor.
Oh, thank you. Is that a buy or a